Good evening, y'all. Welcome back to another Sunday night Electronics Bash Fundamentals of Arduino stream. And as I finish futzing with the camera, as I always seem to be doing, it's good to be back on another Sunday night. It has been a week, y'all. I'm sure you don't need to tell me to tell you that. Again, evidenced by the fact that, as Mike points out, this is week number 11. Not week number 10. Couldn't even be bothered to update the lower third. But thanks to the magic of technology, we can fix that right there, and then the only people will know. Maybe I'll edit that out in post, and there'll just be a little treat that only the people who saw this live will get to know. Probably not. I'm not going to bother doing that. Yeah, welcome back, y'all, to another little Sunday night escape as we talk about Arduino and code and electronics and all kinds of fun things. I am looking forward to tonight. I didn't realize when I sort of picked this topic last Sunday that this Sunday is kind of the antithesis of what we did last week. Like last week, for those who were or weren't here, was all about code, right? It was sort of my second attempt at like, how do you teach code on stream? Which I thought was fun and interesting, a little dense. Like it's always going to be kind of dense to talk about something that's a written language, but I thought it was fun. And so this week we're actually going to be writing very, very little code. Today is all about, and I don't think this is a spoiler for anyone. Today is all about how do you take your project that you built with your nice big Arduino and turn it into something that you can install permanently somewhere, and various options for doing that, and sort of making it a more rock solid option rather than this, which is meant to be a prototyping platform, make it be very easy to modify. But of course, when you're doing something permanently, you don't want it to be easy to modify. So we'll go down a few avenues related to that, which I think will be a lot of fun. But as always, we'll give people sort of one more minute to catch up. Our lovely moderator, Kenneth, has let me know he's not with us tonight. He's hanging out with family, which gives me impunity to just sort of be wrong whatever I want to be, because Kenneth is so often in the chat correcting things. But keep putting questions in the chat, as always, or comments, or like, oh, I tried this once, or what, could you do that, or could you do this? Because I always think questions and comments are interesting. Even if Kenneth's not going to be jumping in to save my butt to answer them, I'll do my best. And we'll see where tonight goes. I should say, holy cow, that's good. Tonight, my drink of choice is a whale tickler, which is a double IPA with mango from Spiteful Brewing Company just up the street from us here in Chicago. It is so good. It's wildly good. It's also 9.1% ABV, so this might end up being, and it's a tall boy, so it could be end up being just a little bit of a goofy night, but that's all right. Like I said, probably easier to do like the wiring and circuiting part of things than the coding part of things if you're drinking a double IPA tall boy. So hopefully everything will turn out just fine. But I was always curious to hear what you're drinking out there. If you're hydrating, if you're doing, I know that whiskey sours have been popular in our house. That's kind of shaping up to be the drink of the summer. We're planning for a little Cajun night next week with maybe some hurricanes. I don't know. What are you all drinking out there tonight? And as you let me know, I'm going to dive into the meat of it right now. So, oh, come on. Open the thing. There we go. So, tonight's theme is, like I say, making it permanent. I'm going to fiddle with this camera too, because I just can't help myself. There we go. So the thrust of tonight is, so this Arduino, especially this Arduino Uno, which is almost certainly what everyone has been working with as like their first Arduino, which is awesome. The whole point of the Arduino is to be a prototyping platform. It's meant to be really easy and fast to connect and disconnect things, reprogram it, make it fast to like whip something together and remove a lot of the barriers to entry that existed before the Arduino platform, where you would have had to solder something or clip something or try and get you to your first 6 projects as fast as humanly possible. And that's really cool. And as we've talked about, we have these connection points, these female header connections that make it really easy to just take a bit of wire and push it on in, and all of a sudden you have an electrical connection, right? Or you unplug it and it's done, which is a really great feature. Like that makes it really easy to whip stuff together. But unfortunately, let's say you make something really cool. Let's say you make something like our build together project like we did last week that was like the world's scariest fire alarm sensor system, or some kind of lab instrumentation, or anything you can think of to build with this. If you build it with an Arduino Uno, you will have been able to build it very quickly. But unfortunately, if you have a wire that's simply stuck into a header, there's not a whole lot inside your box unless you're really going wild with the hot glue or the staples to prevent this from just pulling out in the field or on your workbench, and now you have a broken device, and that's not. I assume that's not what you want. Maybe you wanted a particular challenge and wanted to break it yourself, but in general, we don't like broken things. So tonight's theme is how do you go from this form factor, which is meant to be good for rapid prototyping, to another form factor, little teasers here, that are better for permanence and have some additional benefits along the way. So here's a few of the things we'll be looking at tonight. How do you transfer the microprocessor from the Arduino to a breadboard or a protoboard? And we'll get into sort of like what the microprocessor part of the Arduino is in a second here. We'll look at programming the microprocessors themselves, and soldering to a perfboard or protoboard to sort of make these products a little bit more permanent. And then as sort of the wrap up of our night, we'll look at sort of smaller and cheaper variants of both the Arduino platform and of the microprocessor that's on it. So if you want to do a project that you don't want to tie up your Arduino in, or you just don't need that much capability, there are cheaper, less expensive options that we can program in a very similar way. And so we'll look at that sort of at the last part of our evening. So first, let's ask the question, why might we want to dissociate ourselves from this form factor? And one of the things that I touched on, which I think is a big reason, is durability. Like, this is meant to be easy to plug and unplug, which is great for the experimentation part of things, is not so great for a durable installation. Cost is another, like the name brand ones of these cost, I don't know, 10, 15, 20 bucks nowadays. Even the off-brand ones, 8 or 10 bucks. You can buy, though, just this chip, just the brains, the microprocessor part of this, for a couple of bucks. And it does, this has all of the thinking and processing. We'll get into exactly what this chip is in a little bit. You don't get the rest of this peripheral, so it's sort of up to you to do a little bit of extra legwork to get the thing working. But if cost is really the object that you're trying to optimize, you can buy just this chip a whole lot cheaper than you can buy the whole Arduino. And as we look at those sort of smaller variants at the end of the night, as you go down in size, capability, and connection points, you really can start cost optimizing. So whether it's, I bought this for 20 bucks, I don't want to lock it up inside of a case in my fish finder that I built. I want to keep it on my workbench to play with. There are cheaper ways of getting the same functionality and not having to give up your prototyping platform. Flexibility is another one. There are some things that are baked into the Arduino, like how the power is delivered to the microprocessor and its connectivity options, and the fact that it's got female headers instead of, say, screw terminals or lugs or something else or solder points that you might use to attach to. So when you're building one of these systems up by yourself, you can make some choices about those systems that you wouldn't have available to you if you were just building on top of an Arduino Uno. Power saving could be an option. Power saving and low power systems will be a topic for another day in its entirety, because it's kind of a cool topic. But there are some parts of the Arduino that are constantly, if you're even doing nothing with the brains of the Arduino itself, there are parts on the Arduino board that are burning some power, and you may not have the power budget to constantly be losing that power if you're in a very limited battery situation or a solar power situation. And so the ability to sort of build your own system up gives you the ability to rethink what your power budget is in your project. And then also for fun, for learning. We're going to learn some more about the heart of the Arduino by doing this, and so that's always a good reason to start taking things apart and building them back up. So I want to talk briefly about the parts of an Arduino Uno itself that we've seen so much. Let me see if I can, rather than doing this on the slide, I'm just going to zoom in here to this one. Let's see if we can get it in the light there. That's pretty good. I've got my pointing stick. So as I sort of alluded to earlier, that seems to be in pretty decent focus. Is that pretty decent focus? Yeah, it's not bad. As I sort of alluded to earlier, this chip here is the brains of the Arduino. So this is in this case, an ATMEGA 328P, I believe is this variant. So what does that name mean? So ATMEGA is a product line from a company called Atmel, who 4 or 5 years ago was bought by Microchip Semiconductor, but everyone just calls them Atmel chips still because they were made by Atmel for 30 years before they were acquired. So ATMEGA is a line of chips that they produce. This is the 8 series. So confusingly, as we'll see tonight, a lot of the chips are sort of they have a last name and a first name, so to speak, and much like at least in English-speaking countries, I know this is an Anglo-centric point of view, your last name tells you what sort of broad family you're in, and your first name tells you what specific unit you are, for lack of a better word. So you will often hear these called an ATMEGA 328. It's more accurate to say this is an Atmel 32.8. It's in the 8 family, and it's the 32 variant. So there is an Atmel 16.8. There's an Atmel 8.8, and they are all very similar. They are all in this same package. Typically, the differences between different members of the same family is how much internal storage do they have. Almost all the various Atmel chips will have separate storage for your program and for the data that your program uses, and they're sort of classed differently. But say the ATMEGA 32.8 has 32 kilobytes of program space. The 16.8 has 16 kilobytes. The 8.8 has is 8 kilobytes, and so on. So it's good to start thinking about this not as a 328, but as a 32.8. And we'll see some other families and variants as we sort of get a little bit later into the night. Spoilers. So this, in very real sense, is the brains of the Arduino. It does all of the thinking. It's where our program lives, it's where our data lives. And so this is the full schematic of an Arduino Uno. We're not actually going to stay on this slide. This is just to make the point that there's a lot of useful stuff on this board that does useful things for us, but a lot of it is overkill if you're just going to put this thing inside of a box and put it on a trail to control your trail camera, or build it into your frequency generator and like be the brains in there. If you don't need all this functionality, it's kind of a waste to leave it sitting there doing nothing. So let's zoom in on just the part of the circuit that is the sort of the essential brains of the ATMEGA 328. This is ripped straight from the data sheet. And it's labeled, for now, with the names that we've come to identify with the various Arduino pins. So we know our digital pins, D0, D1, D2, and so on, all the way up to D13. We have, here, let me get a little bigger here. There we go. We have A0 through A5, and so on. And you'll see there are some ancillary points of connection on this chip as well. VCC we've seen before. Remember, that's power, so that'll be 5 volts that we have to put in this case. There are, I should say, 3.3 volt variants of many of these chips. We're just going to be working in a 5 volt universe for tonight. So a couple of different places on the chip where you have to put 5 volts in. This AVCC is the power supply specifically for the analog sensing part of this circuitry. And it's broken out into a separate pin to give you a chance to really make sure that is a rock solid 5 volts exactly power supply, or at least a rock solid whatever voltage it is, 4.9, 5.1, because the way that the analog input circuitry works, if there's any wiggle or wobble or sag or boost in the power supply that supplies them, it will affect the accuracy of your analog readings. So they give you a sort of a general power pin, this VCC pin, and then this AVCC pin is like, all right, if you have to choose one pin to make a really rock solid power supply with no ripple on it, put it on that pin. We have a couple of ground pins here. And then we have a couple of pins here. In this case, they're little XLAT1 and XLAT2. They're called a few names, and we'll see this over the course of tonight. Connected to this 16 megahertz crystal with a couple of 22 picofarad capacitors to ground. And that, if we're looking on our Arduino, is this guy right here is our 16 megahertz crystal, and there are a couple, I would guess, I think it's that one and that one, are two little 22 picofarad capacitors to ground. That forms the oscillation part of our circuit. We've talked a few times over the weeks that the Arduino itself is sort of running at 16 megahertz. It's doing 16 million fundamental operations per second. And a fundamental operation isn't necessarily the same thing as a line of code. In fact, usually a line line of code will be doing sort of 2 or 3 fundamental operations under the hood at a sort of more primitive level than our code operates, but it's able to do 16 million of them a second because this crystal oscillates at 16 megahertz. And by that I mean, a crystal in and of itself is actually a very small slice of quartz crystal that is ground down to a very specific size and shape. So when you excite it with just a little bit of electrical energy, it will tend to vibrate at a very specific frequency. Much like a tuning fork doesn't oscillate on itself, but when you, say, hit it with a bell or strike it against a table, it will oscillate at one particular frequency. A quartz crystal oscillator operates in the same way. And the 2 small 22 picofarad capacitors there are there to sort of support the crystal's oscillation. They are designed to match what's called the load capacitance of the crystal, and they're necessary for the crystal's function, I guess, is the primary point for our purposes tonight. So in order to run our Arduino at its sort of maximum speed, our 16 megahertz speed, we need this external quartz crystal to even get the thing cycling through. There are a few other bits and pieces here, but I want to highlight that there are some pieces here that are not, strictly speaking, necessary. It is common on most, if not all, Arduino boards and variants to have a little switch that's connected to the reset pin here, way up at the top, that when you close that switch, when you pull that reset line to ground, resets the Arduino. Super handy thing here, and the R3 has one. It's this little button up here, is tied directly to ground. Not, strictly speaking, necessary, so if we're building one up ourselves, we can leave that functionality off. The resistor between VCC and reset, this 10k ohm resistor about, 5k or 20k would be fine, but a high value resistor from 5 volts to the reset line is a good idea, not strictly necessary, and by that I mean I have programmed variants of the Arduino without this resistor in place. It is a good thing to implement, and resistors are cheap, so it's a good idea to have it there. And finally, this little down here, we've used our built-in LED on the R3 several times to like flash out or just see that things are working. Of course, you can add a built-in LED on pin D13 to mimic the Uno, just like with any other circuit. But you don't have to. So really, when we take away the optional parts, we're left with really to get this ATMEGA processor running and running our code and behaving like an Arduino. The pieces we need are the chip itself, the crystal, 2 capacitors, and it'd be a good idea to have this 10k or so resistor to 5 volts, this pull-up resistor to 5 volts, that holds that reset line high and prevents the Arduino from just resetting itself accidentally. And that's it. We have a couple places to connect to power, a couple places to connect to ground, but the circuit, just a basic circuit for running code doesn't take a whole lot of ancillary parts, and that's super cool. So what else, what are we giving up? Like why, if that's the case, why is there so much other cruft on this board? So other things that are on the board that you're sort of giving up by building your own system in this way, things that we've cut out of this schematic diagram, I think is a way to put it. So we don't have a programming interface anymore, and that is, for example, on the Uno, this little chip right here is actually another ATMEL microprocessor that is specifically taking responsibility for all of the USB communication and translating that into essentially serial, which we've talked about before, sort of one line for transmit, one line for receive, in a form that the Arduino chip can understand, the ATMEGA 32A can understand. So there's another microprocessor on here just handling USB communication and some support components, so some capacitors and resistors that need to make that controller work. There are a couple of smoothing capacitors here that we can choose whether we want to add or not. We talked about last week, I think, or a couple weeks ago, I can never remember anymore, that adding capacitors between the power and ground side of your circuit basically acts like a little bucket of charge to allow your circuit to, if you're having a particularly intense moment of power draw, that capacitor can give a little bit of charge back to the circuit to sort of supplement the power supply in moments of high draw. And then in moments of lower draw, it can absorb some charge back into itself and store up charge for the sort of next high current event. So we can choose whether we want to add them or not if we think we're going to be doing sort of high power things, but not strictly speaking necessary. Another thing that we potentially given up is there's a voltage regulator on this Arduino. We've often been powering ourselves from the USB port, port, but you can shove between 7 and 16, 20 volts DC into this barrel jack or into the V-in pin, and this voltage regulator, like we talked about a couple weeks ago on the battery session, takes in a more or less arbitrary positive voltage and converts it to 5 volts by burning off the excess voltage as heat, so to speak. So our sort of rudimentary schematic here doesn't include a voltage regulator, so we're going to need to figure out how are we going to get 5 volts into this thing. We could add our own voltage regulator, certainly possible, but again, if we're trying to scale this down to the bare minimum, that is one thing we're giving up. And then there's other little niceties that we sort of have marked as optional here. Things like this LED on pin 13. On the R3 on the Uno, there is an LED that just turns on whenever there's power. There's a little green LED, which is a great feature. Do you need it in your circuit? It's really handy, but you might not. You might choose to leave it out, or you might decide that, hey, like those 2 milliamps of current are more than I want to be spending on my project because it's got to run off of batteries and every milliamp is precious. So we can choose to leave that in or leave it out. And then other things like a reset switch or connectors or things like that are things we might want to think about whether we need to add or whether we need to not to. But at its core, this is the fundamentals of an Arduino. I guess I should say, just to make it totally clear, these Atmel microprocessors, like the ATMEGA, existed quite a bit longer than the Arduino has existed. The Arduino project, which was an offshoot of a project called Wiring in 2004, 2005, the purpose was, before, to program one of these chips was kind of cumbersome. You needed some specialty external hardware, you need some specialty software on your computer. The form factor is not particularly approachable, and you need power, and you need this crystal. And so it was the people who are sort of coming up with the idea of an Arduino, of a sort of a hobbyist microprocessor, said, what if we tried to make it as simple as possible for someone to take this thing, plug it into their computer, write some code, and put it on the device and just run it. And that's what this platform is designed for. So really what they did is they took this processor, which has all of the capabilities we've been using, toggling digital pins, analog input, pulse width modulation output, serial data, all kinds of things. Those are all inherent to this microprocessor and existed before the Arduino ecosystem did. What the Arduino project with Massimo Bonzi and others did was take this processor and say, how can we make those capabilities as easy to access as possible? So really, when we're writing code for the Arduino, what we're doing is writing code for one of these processors, one of these ATMEGAs or a similar variant that's just wrapped up in a nice bow for us. So for today, we're going to take the bow off, do away with some of the niceties, because it's going to sort of benefit us in ways we talked about earlier, saving cost, complexity, allowing us to make choices about permanence and things like that. So that's what the microprocessor is. It really is the Arduino, and everything else is sort of supporting components. Cool. Questions? Does that sort of make sense? I know we're getting a little bit deep down the circuitry and nerd rabbit hole here, but this will be a fun night. I think this is a good way to sort of refresh our wiring abilities and our electronics abilities. That's so good. It's strong. It's strong. It's gonna be a night. Ah, so tasty. Where do we go next? Oh, so here's a good point. So these pin names, D1, D2, A5, and so on, are names, are monikers that the folks who were originally coming up with the idea of an Arduino came up with, because the names that are given to the points of connection on the microprocessor itself reflect the underlying architecture of how its internal hardware is built, but aren't necessarily like the most approachable. And to show you what I mean, so this is a diagram of the Arduino pin names in red down the left and the right, and these sort of the internal names, or what Atmel would say that these are called, in the black in the middle here. So we can see all of the pins are present. Ground and VCC, AVCC, and ground, all very much the same. But for example, something like analog input 3 is actually PC3. Digital pin 1 is PD1, but digital pin what is this down here? Digital pin 9 is PB1. And those reflect sort of in the core of the device itself where the information is stored about whether pins are on or off, whether they're inputs or outputs, are stored in a specific set of ways. But, I think reading something like digital 1, digital 2 is a lot easier than remembering that that's PD1, which is also PCInt 17 or TXD, right? These are sort of more complicated names. So the Arduino developers, these sort of initiators, came up with a sort of like, well, we're going to sort of wrap all those ideas into a more cromulent set of names that are easier for someone approaching the device to understand. And I think they did a pretty good job. But to unlock a little bit of this functionality, now that we're getting inside under the hood of the Arduino itself, finding some of these more sort of internal names, the names on the chip itself, are actually really helpful. And in fact, there are several of them that are going to be most helpful to us tonight. So let's look at those real quick. Obviously, VCC and ground and a VCC, right? We're going to connect to 5 volts and to ground. Hopefully that's not too crazy of a thing. So 2 points that need to be grounded, 2 points that need to be connected to 5 volts. If we're doing analog measurement, this AREF also needs to be connected to either to 5 volts or to the maximum analog value you'd like to measure. So when we were doing analog measurement back in week 2, which I think is now 2 months ago, we were always measuring things out of a possible maximum of 5 volts. You can reference your analog measurements to lower voltages. If you wanted to say, hey, my highest voltage that I'm ever going to be measuring on any of these analog input pins is 3 volts, and I'd like some higher accuracy in that range, you can set this analog voltage reference pin to put 3 volts into that, and that will sort of scale down your voltage reference range. But by default, connecting this to 5 volts is not a bad idea. Right? So for so far, power, ground, nothing too crazy. Down here, pins 9 and 10 on our chip have many names, PB6 and PB7 and so on, but what I want to look at, they're denoted as XTAL1 and XTAL2. These are the places where we connect our crystal, our external oscillator. And remember, we're going to connect a 16 megahertz oscillator between the two of them, and then from each of those points, we're going to connect a 22 picofarad capacitor to ground. I should say, because I think I haven't tonight, for anyone who's just newly joining us, all of these slides that we're looking at tonight are linked to in the description and also on the website, which is over here. Jeff.glass/electronicsbash. There is a page for this week's episode. It links to all the slides. And the page this week also has a full shopping list of all of these little ancillary parts that we're going to be talking about tonight. From some feedback we got a few weeks ago, I know one of the goals of a lot of people right now, and I totally get it, is to try and avoid like investing in a whole lot of new kit, because we're all being very conscious of how we spend our money these days, which is great. Go and check out the prices on some of this stuff. Like some of these chips are a couple bucks or $1. Shipping is really cheap. And the crystals are super cheap. I put links both to Amazon and to DigiKey on the website. DigiKey is an international parts supplier that stocks millions and millions and millions of things. So if you... And their prices are often better than Amazon. You do usually have to pay for shipping, which if you're Prime, you don't, but... it is worth it even if you're buying, say, $10 worth of things to get them from DigiKey for $10 as opposed to Amazon for $20. They're really, really cool. A website worth poking around. They really do have a little bit of everything. But maybe DigiKey sleuthing is a topic for another night. How you find electronics parts. That might be kind of a fun thing to do. Also, reading a data sheet. Like once you're looking through a list of 300 of these, very similar looking chips, how do you decide which ones have the functionality you want? That might be a little beyond our scope tonight, but that'd be a fun topic for another night, I think. But we'll see. Where were we? Oh, so slides are on the website. Shopping list is below on the description or on the website as well. One of the things you would need if you want to sort of divorce your Arduino chip from your Arduino board, in addition to the chip itself, is a little 16 megahertz crystal oscillator. These things are so dirt cheap. Like 25 cents a piece. They're so common. You can get crystals in all kinds of different interesting frequencies. Here's my bag of 16.0015 megahertz ones for some reason. Here's a crystal at 1 megahertz in kind of an old form factor. All kinds of fun things and fun frequencies that have sort of been ground to vibrate at those specific frequencies by the manufacturer. But these 16 megahertz ones, like super dirt cheap, you can get a pack of 10 for a couple bucks. And they are sort of one of the essential components if you're building sort of an off-board Arduino here. So maybe this is a good time to say, I am currently building up sort of this circuit that we've been looking at with the ATMEGA chip, the crystal, and various things on this breadboard here. So I've got my ATMEGA chip here. I got my 2 points where I've connected ourselves to what's going to be our 5-volt line, these 2 red wires here. I've got my 2 points where we're going to connect to ground, these little white wires here. I've got my 16 megahertz crystal connected to 2 pins right next to each other, that XTIL1 and XTIL2 pin. And they're connected to ground with these 2 little adorable 22 picofarad capacitors. Aren't those super cute? Super adorable. And I've chosen to put a 10 kilo ohm resistor from the reset line to positive 5 volts. And like I say, this is not strictly speaking necessary, and that it will probably work, but like 10K resistors are a dime a dozen. That's not even true. They're like a cent a dozen. So I threw one on there because it really can't hurt. So those are the pins we've probably recognized from things so far. The sort of known connections: power, some connections to some crystals. There's 4 other points of connection that I want to highlight here with specific names, and I'll show you where they are on the ATMEGA 32.8. As we look at other chips later in the evening, they're going to be in different places, but the names will be the same. And those names are highlighted in blue here. This reset pin, that's the one that I've pulled high with that 10K resistor. That reset pin, if you pull it low, resets the chip, sort of holds it off until it goes back high. When you press your little reset button on your R3, all it's doing is saying, hey, when that pin goes low, the processor knows, hey, wow, we're going to start things all over from the top again. And when it goes back high, we start the code rolling from the beginning. So we're going to need to connect a wire from our programmer, which we'll get to in a second, to that reset pin. So we can tell the processor, hey, stop what you're doing. I'm about to be sending you new code. I'm going to pull your reset line low. So we'll need a connection to our reset pin from our programmer, and we'll get there in a hot sec. We'll also need connections for our SCK pin, which is our serial clock pin, and to 2 pins called MOSI and MISO. MOSI and MISO are acronyms or anagrams, if we're going to pronounce them like that. They stand for master out, slave in, and master in, slave out. And these function a lot like the shift registers we were playing with in week 9, week 8, week 9, 7? Who can say? In that, when the serial clock line goes from low to high, the Arduino is going to load in 1 bit, 1 or 0 bit of data from the line that is the master out, slave in line. And that sort of makes sense, right? If we're programming this chip in a little bit from an external processor, those bits are going to be coming from a master, from a programmer, and into the slave. Master out, slave in. And at the same time, it's going to put a value of 1 or 0, 5 volts or ground, onto its pin that's master in, slave out. So you sort of have this potential for bi-directional communication. And the Arduino programming environment is able to make use of both of those, both to upload the code by sending code out of its master out into its slave in, and getting some checks back after the code's been uploaded to say, like, hey, did I actually upload this successfully? So be reading bits back from the master in, slave out line, just to make sure that everything's coming back okay, that everything was written okay, or that was erased just fine. So we'll end up connecting to both of those points. So there are 4 total points of connection that we'll need from our programmer to the target chip, which will be the reset line, the serial clock, MOSI, and MISO. So for our programmer, and this is a really cool thing, we're going to use the Arduino R3 that we've had on the table this whole time. And this was a project that was not originally a part of the original Arduino scope and goals, but a few years after the project became popular, people were saying, hey, it's great that we have this environment, but I need some external tools to sort of set up this chip to be an Arduino processor and be able to accept Arduino code natively. It's a shame I can't do that with an Arduino. And somebody else said, well, why can't we do it with an Arduino? So now we have the ability to program other chips directly using the Arduino as a programmer. Specifically what's known as an in-system programmer, or an ISP programmer, you'll sometimes hear them called. Sometimes ICSP, in-circuit serial programmer. I think the two are interchangeable. And that just means you have the ability to hook up some wires from one device, in this case our Arduino, to our target chip and program them directly without some kind of additional hardware. We can program this chip in the circuit, in the place where it lives, without having to pop it out and expose it to a higher voltage environment or reset it with UV light. The first generation, and still today, some resettable memories, you had to sort of expose the chip on the inside of this through a little window on the top with UV light, and that would clear the memory out. None of that's necessary. We can program this in the system wherever it's living, which is really pretty cool. So we're going to use the Arduino to do that programming. And I said we were going to need to make those 4 points of connection between our programmer, our Arduino, and the target chip. How do we know? So we found those places on the chip itself that we're going to have to connect: reset, serial clock, MISO, and MOSI. Where do we connect those two on the Arduino? Well, if we look at our Arduino pinout diagram, and this is just from our www.arduino.cc, like the Arduino website. This is their little map of where things live on the Arduino. We can zoom in a little bit here, and now we can zoom in a little bit further, and we'll see that some of the digital pins that we know and love are also labeled SCK, MISO, and MOSI. And those are exactly the points that we're going to hook up to the serial clock, MOSI, and MISO pins on our device. And I should be clear, the MOSI pin on the Arduino connects to the MOSI pin on the target chip. The MISO pin on the Arduino connects to the MISO pin on the target chip. That's part of the goal of this naming convention of MOSI and MISO, rather than transmit and receive. Because with that kind of terminology, the question is do I connect my transmit pin to your receive pin, or does your receive pin match to my receive pin? And it doesn't matter. We have a master out, slave in, right? So the MOSI matches with MOSI, and the master in, slave out, MISO matches with MISO. So we'll be making connections from pins 11, 12, and 13 to our MOSI, MISO, and serial clock pins. And then for my example today, I'm going to be hooking the reset pin up to digital pin 10. This is we'll see in the example code, this is sort of the de facto standard, but the reset pin is really only used at one time in the program sequence, sort of to pull that pin low, let that new chip know that new code's coming at it, then it goes back high. So it can be set to be any digital pin. I'm going to make use of pin 10. You'll often see examples floating around online of hook these up very specifically to pins 10, 11, 12, 13. 11, 12, and 13, MOSI, MISO, and serial clock are critical. Pin 10 as reset is just kind of convention by now, but you could use anything else. So when we put all that together, this is the circuit that we're going to build up. And I should say again, the slides are on the website, jeff.glass/electronicsbash, so don't feel the need to memorize this now. Pull this down when you need it. But we can see we've hooked up our virtual chip here to power and ground in 2 places. We've connected our crystal with 2 capacitors to ground as well. And then we've hooked up our 4 connections. Our reset line goes to that first pin 1, MOSI, MISO, and serial clock are these next 3 pins down here connected to digital pins 11, 12, and 13 on the Arduino. So let's go ahead, we'll make those connections, and then I'll show you how to use the Arduino as a programmer to program that chip in that setup. So I've got my Arduino here. I've got this glare thing going on that I really need to fix. Let's do that. And we'll zoom out a little bit, and I might just see if there's anything we can be done. That helps a little bit, I think. There we go. Futzing with cameras seems to be just about all I do now. So first things first, I'm going to hook up one of the ground pins over on this side of my Arduino to the ground rails of my breadboard here. And I've got a ground rail here connected through this white wire to the ground rail here. Remember that by default, the blue and blue are not by default connected. Red and red are not necessarily connected, but in my situation, I've just bridged them with a bit of wire. I'm also going to hook up the 5-volt line from my Arduino here. 5 volts. Goes into the power rail at 5 volts there, right? So those will be my power connections. So now I'm going to hook up my reset, MOSI, MISO, and serial clock lines. So from pin 10, I'm going to hook up to my reset line. That's pin 1 up here. That's where that resistor has been hanging out this whole time. Probably stand to zoom back in just a little bit. There we go. Then I'm going to connect my MOSI pin, which I believe is pin 11, although thankfully I made slides and double checked. Yes, MOSI will be pin 11 here. And on my my target chip, my ATMEGA 328 that I'm playing with on the breadboard here, that'll be pin 17. So 3 up from the bottom, down on that side. So I'm going to connect my MOSI pin to 1, 2, 3. Connect that there. There we go. Pin 12 on my Arduino Uno, the MISO pin, connects to the MISO pin on my target chip. And pin 13, my serial clock on my Uno, connects to serial clock on the target chip. And there is my programming setup. So this is going to allow me to flash some code onto this target chip using the Arduino as a programmer. So how do we set that up? I will show you. That's what I'm here to do. When I get a little goofy, it's time for a little beer break. It's amazing to me, even in these humid summer days, how dry my throat gets just talking for like a couple hours. So I'm gonna try and do better and keep things nice and hydrated. Oh, that's very good. So to use the Arduino as a programmer to program additional Atmel chips, there is a program that comes with the Arduino IDE that we can use called Arduino ISP. It's in your file menu of your IDE. Under, I know it's hard to see that little tiny font size but down at the bottom of the built-in examples, there's a little sketch called Arduino ISP that you'll load up. I've loaded it before. I had to change a couple things, so I have a separately saved demo version here. But this is exactly the same stock code that comes with your IDE, and it even tells you a little bit about which connections to use. This says pin 10 is used to reset the target microcontroller. On some Arduinos, MOSI, MISO, and SEK are the same as digital pins 11, 12, and 13, which is a very helpful note. It reminds you how to wire these things up. And then it tells you if you're doing a lot of these, you can add some LEDs to other digital pins that give you some status updates as things are uploading. You can use this heartbeat pin to tell you when the program is running, a light that'll light up if there's an error. Like, they've really done a really nice job of writing this little slice of Arduino code to give you some feedback as you're uploading code, if you want to. I haven't done any of that currently because it's a little bit overkill, but you can. If you're having troubles, if you're doing a lot of these and you just want to know something's working all the time, this is a useful bit of thing. I should say also, as we get into programming some of these, I'm going to show you sort of multiple ways to do each of these things. Some of them focus on, like, if you're doing this for ones or twos, or, you know, I want to build one thing, I just don't want to put my Uno inside it. I'm going to program one chip and be done. Really simple and fast ways to do things. I'm also going to show you over the course of the night, if you're doing this so that you can cheaply build 10 of a thing or 100 of a thing, you're going to be repping through these over and over and over again. There are some construction techniques and some programming devices that will make that kind of scale a little easier and faster. Not something you need, right? Like, my goal is, like, let's get this thing working as soon as we can. But I'm going to show you some, like, little bits and pieces that, like, if you're going to leap in and be like, ooh, I'm going to use this new knowledge to build 100 LED fireflies that run off an Arduino. Super cool. There's some tips you can use to make that a little bit easier than hooking up 6 wires to your breadboard every time you do it. So, but we'll get to that in just a little bit. So this Arduino ISP code is just a bit of Arduino code like any other, and we can upload it like any other. So I'm going to plug my USB cable into my Uno there. I'm going to select my COM port, COM11, as in Arduino Uno, which is right. And then, just like usual, I'm going to upload that code. So I'm going to hit the upload button here, or in my tools menu, hit upload, or hit Control U on my Windows machine. I think Command U on your Macintosh. You may also notice down here, this lower section may look a little bit different than yours. I have turned on verbose notes when things are being programmed because I was having some strange driver issues earlier. If you want to do the same in your Arduino preferences, wow, you just can't see that at all. I'll just tell you, there is a button in here that says show verbose output during, and if you check the upload button, it will show you lots and lots of things. It'll show you when it's reading, when it's writing, what it's discovered. Again, not necessary, but if you have weird issues like I did on an ancillary project, can be useful. But anyways, at the very end it says AVR2 done, thank you. Well, that's very nice of it. So now I've loaded this code the code that turns the Arduino into an Arduino programmer onto this Arduino, right? Now I can use this Arduino to program this chip to act like an Arduino, and here's how we do that. It's a two-step process. The first thing we're going to want to do is burn what's called the bootloader to the Arduino. What is a bootloader? A bootloader is a small bit of code that helps a processor run more code. So in our case, you may notice we have to hook up 4 separate wires to this Arduino to load code into it. But we've said before that to get code onto the Uno, we're really only using the serial lines, the TX and RX of the serial communication from this little ancillary chip here. This processor by itself is not designed to take in data from the serial communication lines in that way, but we can load a little bit of code onto it that says, hey, listen for things coming in on the serial line in this way, and write those into your memory like we were doing the full code programming setup. It's kind of like we have a really, this is maybe a tortured metaphor, tell me if it's awful. I mean, or don't, spare my feelings. But let's say you have a really annoying coworker who only takes instruction via email. That's all that this coworker knows how to do, and won't budge from it. And one hack you might employ is to send that employee an email which says, please obey all verbal instructions from the boss. And that employee, as a good employee, will say, all right, well, now I accept verbal instructions from the boss. But that employee had to be told via email first what to do. In a similar way, this chip doesn't by itself know how to take commands from a serial console over USB, but we load just a little bit of code onto it that teaches it how to do that, and then it's happy to load code over serial from the USB in that way, and that's what the bootloader does. There are a few other things going on when you burn that bootloader, I should say. One of them is configure the chip to use this external crystal. There are other options that don't involve using a crystal that are slower or less accurate. So one of the things that it does, right, when you do a bootloader burn for the first time, is set some configurations inside the chip that say, this is what kind of chip you are, this is what kind of oscillator it's going to be connected to. I want to leave your memory open to later programming. There are configuration options for, hey, lock down your code and don't ever be allowed to modify it again, which is obviously what we don't want. So we're going to clear those configuration options, things like that. So we always want to make sure we're burning our bootloader before we use the chip the first time, because it will set up this chip to be programmed and it will set all those options correctly. After that, you can just load code, and so on. So, and I should say, even if you're not going to be using a serial line to program your chip, even if you're always going to program it like this with a bunch of external wires, you should still burn the bootloader in, because that will make sure you set those settings correctly. Capiche? So, burning the bootloader could not be simpler. You're going to come up to your Tools menu, and in your Board menu, you're going to select the kind of Arduino that has a chip that matches the chip that you're using. So not the Arduino that you're programming with, but the actual chip itself. Now, for our purposes, we are using an Arduino Uno, and we're programming a chip that's just like the chip from an Arduino Uno, so I'm not going to change anything. But we could just as easily be programming a slightly different species of controller that's usually associated to like an Arduino Mini or a Leonardo or a Nano or these other things, which are all very similar with slight configuration differences. And if you were doing that, you'd want to choose a different board type. But I'm going to leave mine, and I know you can't see it, so I'll narrate for you. I'm going to leave my board set to Arduino/Genuino Uno here. And then in that Tools menu again, I'm going to select my programmer. I'm going to select down here at the very bottom, I'm going to say Arduino as ISP. You can see there's all kinds of different programming options you have here, which refer to various other hardware devices you can use to program various Atmel chips and other microprocessors using various bits of hardware. We're going to use the Arduino as our in-system programmer, so we'll select Arduino as ISP. And then finally, in our Tools menu here, we'll select Burn Bootloader. We'll see a lot of things come out here because I have it on verbose mode, but usually it'll just pop straight to "Thank you, done." If it pops to error, then you probably have a wiring error. There's not a ton that can go wrong in burning the bootloader. Especially one thing that I have run into sometimes is a wire being disconnected, or a wire being loose, or a wire being connected to the wrong place on the chip, which is not super duper helpful. actually might have this backwards. Let me double check my connections here. MOSI, MISO, SCK, and on my chip here, MOSI, MISO, SCK. Everything is powered up. Reset and SCK. Let's try that again. All right, burn bootloader. Having us a little hiccup here, but that's okay. Reset is pin 10. This is going to power. Oh, my ground is not connected correctly. That would do it. Helps if things are grounded there. So, like I say, if you're having uploading bootloader error issues, probably a wiring error, worth it to double check the wiring. So let's try that one more time. Burn bootloader. I can see in my display down here, it did all kinds of things. It wrote the bootloader in. It verified that it was correct. It read some data back out to make sure it was all accurate, and then it told me it was done. Super cool. So now I have the Arduino bootloader on this chip, and for all intents and purposes, it is an Arduino. So let's load some Arduino code into it. Let's take a classic example. Let's take our blink sketch that we know so very well, which just turns an LED on and off, and let's pick a pin for it to blink on and off. Just because of the way that my breadboard's laid out, I'm going to choose this bottom right pin down here, which is, in Arduino terms, digital pin 9. I'll show you in the bigger view here. Oops, come back. I'll show you in the bigger view here. This is going to be Arduino pin 9, or what it calls PB1. So we'll make that blink on and off. So I'm going to open up my blink example from just going to File, Examples, Basics, Blink. And we'll all have seen this code before. Looks like I actually loaded this up before and changed the pin to 9 in advance. Very sneaky. All we're going to do is set that pin up as an output, turn it on, wait for a second, turn it off, wait for a second, right? So if I were to just hit upload, by clicking on the arrow button in the top left or going to Tools and hitting upload, that would load the blink sketch onto this Arduino, the programming Arduino, because that is what's hooked up. To load it onto this chip, I need to do one of two slightly different things. I can either, if I come up to my sketch menu, I have an upload option, but I also have an upload using programmer option. And that's going to say, hey, don't load this code onto the device that's directly attached. Use that device as a programmer to program an external chip. So I'm going to use this upload using programmer option. The fast way to get to it is in the top left corner here. If you mouse over the arrow, you get this upload. If you hold Shift, and I know it's hard to see that tiny writing in the corner. Oops, I don't want sticky keys. If you hold down Shift, it changes to upload using programmer. So I'm going to click that there. And that will now use the Arduino as a programmer to write the blink sketch onto this external chip. So now if everything has gone right, and as always on these Sunday nights, I don't guarantee that it has gone right the very first time, I should now have this bottom right here, bottom right pin blinking on and off. So let's just verify that it does. I'm going to hook up a little resistor and LED to that guy, and we'll see if we're lucky. There we go, blinking on and off once a second. So now, in a very real way, this pin, this chip, is the brains of an Arduino. As long as we maintain power to it and leave this crystal oscillator intact, anything that we could do in the Arduino environment, whether that's reading buttons, writing code, controlling shift registers, controlling LCD displays, anything we've done in the past 10 weeks, we can now do with this chip as well, which is super exciting. So remember, the steps were we had to make the connections from our Arduino as programmer to our chip. We had to burn the bootloader to make sure that the settings were correct and it has that little bit of starter code in it. And then we use the upload using programmer option to get the code from our Arduino IDE onto the chip itself. And now the world's our oyster. Questions, comments, issues, concerns? This all sort of makes, I know we seem to be, I always feel like we're going very fast, but I see that we're already 52 minutes in, so maybe that's just my opinion of things. But yeah, is this all making a good bit of sense? I should hope so, because we're gonna complicate it in a second here. As I take a drinking beer is not a hydration break. It's a keep the throat nice and fluid and talkable break. This is a hydration break. Oh, yeah. Ooh, water. So tasty. Great. Assuming this is all making a good bit of sense, and again, stop me, ask questions if it's not. I want to talk just briefly, since the goal of this evening nominally is making things more or less permanent. I want to talk a little bit about ways to take this circuit and turn it into something more permanent. Because of course, this breadboard has the same problems that our Arduino did, in that it's meant to be very easy to plug and unplug wires from it. If I grab a wire here, right? The whole point is you plug the wire in, and now it's connected, and then the wire can come right out, and it's not connected, which is, again, great for experimentation, not great for permanent devices. A breadboard does not belong in an end-user device. I have seen them in many places, in many installations. I have even used them for tools I was using to do debugging in the field, where I knew I was walking into a somewhat unknown situation. What voltage is it really going to be at? Am I going to have to compensate? And I carried a breadboard with some parts on it around in my work bag because I knew I needed to change it very quickly. But for any of the tools in my workshop, any of the permanent installations, this is just not stable enough to cut it. So how do you take this circuit and make it into something more permanent? And the answer is with soldering. There are some pieces of goods out in the world that you may or may not have run into before, that are designed to sort of take parts that have this regular pattern of spacing on them and make them into a more permanent setup. We've, I think, said before, but the spacing of the little holes on the breadboard here matching up with these sort of pin spacing on these chips is not a coincidence. These holes and these pins are all at 0.1 inch spacing, or 2.54 millimeter spacing. That's a fairly standard size for chips that are meant to be interacted with by human hands. Anything that's assembled by a robot can, of course, be much smaller, but 0.1 inch or 2.54 millimeter spacing is fairly standard. We have breadboards with 0.1 inch spacing. We also have perfboard. Perfboard is typically a fiberglass or sometimes a plastic sheet of a small thickness with a bunch of holes punched in it, and either copper or aluminum ringing those holes to give you a conductive surface to solder to. So let me move this out of the way, and I'll show you some random bits that I pulled out of my collection. So here is a bit of perfboard. This one only has metal on one side. We'd say it's only plated with metal on one side. But it's fairly handy. This one's, 20 by 10. This one has a scoring line down the middle, so you could use it as a whole big piece. So you could snap it in half to make smaller pieces out of it. This one, all the holes are not connected to each other, sort of individual. But you can also get perfboard in various patterns where the holes are connected. You can see something like this, which has a pair of things connected down the center, 5 holes connected down the side, and then these strips of linear connections down the left and right side. Something like this is really meant to emulate, in a big way, a breadboard. Or really, they're both meant to do the same thing, which is to make it easy to connect chips with a 0.1 inch spacing to other peripherals. So you can see if I pull one of the chips off of here, it very neatly straddles that center line, so there's nothing touching under here. This pin, if I were to solder it in, would connect to those 4 points, and this pin would connect to those 4 points, a lot like a breadboard would. This one, again, of course, only has metal on one side. This side has no copper, so I'd actually want to install this upside down, so to speak. The chip is on this side, so that the solder connections can be made on the underside here, where the copper is. And these perfboards come in all kinds of different styles. Here's some sometimes called Vero board, where each line is a separate connection point. I think this is another half of that same piece that I chopped off long ago for some reason. Also called vector board, all kinds of different names for this stuff. This stuff, I should say, is dirt cheap. You can get it cheap from Amazon. You can get it really cheap from overseas. I've put a few links to some Amazon products in the description of this video if you're interested in some starting places of some various sizes. But I think I bought a pack of 10 of, so this came with, originally was 3 pieces long. I bought 10 of these for $4. I just had to wait a month for shipping. So worth getting your hands on some if you're thinking about doing this at all. My gosh, is it cheap. You can also now get Adafruit. Adafruit makes a product called PermaProto, which is really meant to emulate a breadboard connection style. And I don't have a piece of this here to show off, but very much in the same way as the board we were looking at a moment ago, it's meant for you to have a space in the middle where your ICs can straddle this middle part of the board. These 5 holes are connected, those 5 holes are connected, and so on. And then you have power rails down the left and right side. So it's really meant to say, hey, I have this circuit working on a breadboard environment. I want to transfer it to something permanent. This allows you to say, all right, well, I'm going to take my exact circuit exactly as it exists in my breadboard, put those in the same holes in my PermaProto, solder them in place, and I know that circuit should work exactly the same way. Kind of a neat idea. PermaProto is just a little bit more expensive, but it makes the transfer process so easy that, like, if you're only building 1 or 2 of this thing, it's a neat investment, right? It makes things really, really simple, especially if you've done some breadboard prototyping beforehand. If you are not using PermaProto or something like that, your other option is to do something like this. This is actually one of the snapped off pieces of this guy. We could spend a whole evening talking about soldering practices. I realize we haven't talked about soldering much, but I'm going to guess that many of you have jumped into soldering a little bit before. If not, we'll talk about it some other time, but I wanted to give you just a little bit of a sense of what a soldered together permanent Arduino setup might look like. So this is a chip socket here, which is meant to take our chip. We press the legs of it down into these little metal holes here that would make solid metal contact, and then we've soldered this chip socket into this piece of perfboard permanent connections. The reason to use a socket is now the chip is removable. It makes it a lot easier for me to say, program the chip on my breadboard, pop it out, pop it into my socket, and if I want to reprogram it, I pop it out, pop it back onto the breadboard, reprogram it, and so on. If I had soldered the chip in place here, I would need to basically find a way to make these connections to my circuit. And I could do that. I could give myself points of connection to attach and disattach, but for many sort of small and temporary things, having a socket in place in case you screw something up is really nice. You'll see later, so this is a 28-pin chip. Is the sort of the base chip here, the 32.8. I didn't have a 28-pin socket. I had 2 16-pin sockets, so I just slammed them together end to end, and I'll have some space left over at the end here. You can see I've got my crystal here and my 2 22 picofarad capacitors. I have my resistor here, which is this same resistor that's pulling up my reset line. And then all the rest of this is wiring for my power and ground. So just like before, I have, let's see, what's our orientation here? Must be like that. I have my 2 places where power and ground are connected on both my devices. I have my reset resistor here. I have my crystal and my capacitors connected in the same place. And on the underside, you can see I've made my various soldered connections. And there are various ways you can go about doing the sort of interconnections between things. For just a few points of connection, this really is not a ton of solder joints for a project like this. I like to use little external top wires. So I've run a little bit of white wire around for the ground connections, a little bit of red for my power connections. If you have a lot of connections, a more common thing to do is do a lot more of your connections underneath. You can take either a little bit of wire or the cut-off component leads from the components that you've shoved through those holes to bridge components under here and then just solder across those various leads. So, like I say, I thought about turning tonight into a bit of a soldering tutorial as well, but given that these things always go about 17 times longer than I expect them to, I figured that might be a little ambitious for tonight. Suffice to say, this is the sort of direction you'd be moving in if you were taking your project from breadboard to a permanent setup. And these sockets hold a chip well enough that you can consider them to be a pretty permanent connection. I say pretty permanent in that, like, if I was gonna, make a temperature and humidity sensor for a truck and strap this to the bumper for 5 years, I might think about putting just like a little bit of hot glue on the chip or something like that to really hold it in place, because it's not permanent. But I feel fine putting a chip in here and tossing it in my backpack for a week. You know what I mean? That's the level of permanence we're talking around here. I'm gonna disconnect power before I disconnect this chip, but let's pop this Arduino in here. Arduino, this Atmel chip, this ATMEGA 32.8 in here, and we'll pop it in the socket. One thing to keep in mind, and this is something that you'll have to judge for yourself when you're making your circuits, we've seen before, like when we did our shift register week, that these chips have a noted orientation. They will either have a little dot in one corner, you can see there a little bit, you can see it flashing, or a little notch out of the end, or both. Will that focus if I get it really close? Kind of. And that defines the orientation of the chip. The sockets you buy will also typically have either a little dot or, in this case, a little notch out of one end, so that when you install your socket on your perf board, you communicate to your later self which orientation the chip should go in. So when I'm plugging my ATMEGA into this socket, I'm going to match up the end that has a notch on the chip to the notch on the socket, and then I'm just going to press it in. A fair word of warning, and you may notice this when you plug your ICs into your breadboard to begin with. The chips as manufactured typically have their little metal, I have so many cameras, the little metal legs here are typically splayed out at a slightly wider angle than is useful for punching into a socket or a breadboard, and you have to sort of manually bend them in. And in fact, when I pull them out of the breadboard, I usually mange them a little bit, so I'm going to use this handy-dandy 3D printed tool from a design that I found to sort of realign those legs. This is not necessary, by the way. You can just bend these, by hand. But just, you want to, don't be surprised if you try and push it in and it seems like the legs are too far apart. That is pretty typical. It's a byproduct of the manufacturing process. You just bend the legs in gently, and then you will slot this directly into your socket. So this is now my little portable Arduino setup. And of course, it still has the same code on it as when it was on our breadboard. So let's finish this thing out. Let's solder that LED into this circuit here, and we'll hopefully have a blink sketch working. And if not, we'll do some troubleshooting. And if it really doesn't work, we'll move on, because that's just how these things go. So, like I said, this is not going to turn into a full night of soldering tutorial, but I figured since this is this solder-heavy project, it would be disingenuous not to do just a little bit of soldering, just so we get the idea here of what's going on. So I'm going to put this in my little PCB vise, which was a Christmas gift, I think, birthday gift. I love this thing. You can find these all over online. They are great. I'm sad I didn't have one before. They're really handy for doing lots of work with little rectangularly shaped things. So I'm just going to steal my parts from before off my circuit board. I'm going to take my LED and my resistor, and I've got to get from this pin to somewhere on this white network here, this network of white wires. So let's see how I want to do that. I'm going to cheat just a little bit because I'm not going to be using this board for anything else. I'm going to use this resistor to bridge the gap, as it were. Make those extensions just a little bit smaller there. My thought in doing just a couple of components here is it spares you the hour it took me to assemble the rest of the circuit, but we're still going to get to talk about some of the tips of soldering to perf board and things like that without it hopefully becoming too boring. So once you've chosen where your component's going to go and you've shoved it through your perf board, one thing you can do to hold it in place is just to reach underneath and bend the leads outward, or in opposite directions to each other. So now that part is more or less held in place because I've bent the leads in such a way, it's a little hard to see there. There's that guy, yeah. So I've bent them outward so this part holds itself in place while I solder it. And since I have a little bit extra of lead length here, I'm actually just going to take this resistor's leg and bend it over to touch the point on the Arduino circuit that I want to connect it to. And I'm going to double check that I connected it to the right place, and of course I haven't, because this is electronics bash and things don't go right the first time, but that is okay because we spot them before we solder. I'm going to bend that leg over so it's just touching the leg of my socket in here, and then I'm going to solder it. Like I say, we should do a whole night on soldering and assembly techniques sometime, but just in case anyone out there has not soldered anything before, some real brief techniques. One, get yourself a decent soldering iron. I use a Heiko FX888D, I think it is. I don't know. It's one of these blue irons with a stand here. You don't have to get one that costs $90. There are some really decent like $40 soldering kits out there. Do not get one of those derpy Radio Shack style soldering pens that plug straight into the wall. They are just no good at all. Interesting. Hang on one sec. I'm gonna figure out what's going on here. Palmer Jenkins for the win. I just got a call from our good friend PF Janky, letting me know that perhaps I wasn't seeing any chat, and Palmer was right. I haven't seen anything since literally 3 minutes in when Michael Trudeau pointed out that this was Arduino stream number 11 instead of number 10. Literally nothing. Wow, that's very exciting. My mic is clipping. It's so embarrassing. All right, well, thank you, Palmer. Thank you for the note. Oh, and Nate is here. Oh my goodness. All right. Well, this is pretty par for the course for a Wednesday night. Wednesday night? Jesus, it's all going to hell. Well, it's good to see what everyone's talking about now. Why don't we finish talking about soldering things? We'll take a little pause. We can see what all the cool chatter is about. I'm so bad. You must have thought I abandoned you. I'm so sad. I thought we'd abandoned me. But we're all just here together. I choose to blame technology. No, pause on the soldering. The soldering can wait. Let's see what's happening in chat. Let's see, Palmer asked if you buy standalone microprocessors, can you put them directly into an Arduino and send them code, or is there some formatting involved? Let's just jam through the questions. Good question, Palmer. You can, after you have burned the bootloader. So once you're in a situation where you have your chip and you've burned the bootloader on it, you can put it into your Arduino here, and it will act just like this chip was, and get programmed. Chris says it's time to start over. Thanks, Chris. So yeah, I was like, there's only 3 messages tonight. It's just quiet. Oh, have you been plotting how to help me in the chat here? Y'all are so nice. Mary has not gotten the message. My God, y'all are so good. Y'all are so good to me. I see most of the questions are, Chris says you can swap the chips. Everyone's taking good care of themselves, and you're taking good care of me. Palmer sent me a text. Of course, I have Do Not Disturb on for these things. Nate says give him a call. Nate, it's so good to see you, Nate. I saw your comment. Thank you for joining us on this lovely Sunday night. I'm glad you can join us live. I hope it's useful and helpful. Oh, my goodness. Well, thank you, Palmer, and thank you, everyone who tried to reach out to my wife and everyone else as to how to get me to know what the heck was going on. But here we are. Oh my goodness. That's about par for the course. I was just thinking to myself, like, wow, other than the lack of chat, this is going really well. Turns out it's going about par for the course all around. Oh my goodness. Well, thanks y'all. I super appreciate it. We're all back here together now, and that feels pretty good. Neat. Well, good. Well, now we can all be together as I rap at you a little bit about soldering things. Where was I? Oh yeah, I was excoriating Radio Shack soldering pencils. The like plug into the wall 25 watt or 40 watt soldering irons for like 15 or 20 or 30 bucks. They're just so bad. It's one of those cases, like, I thought I was bad at soldering for years, for literally, I just was like, oh, I just can't figure out how to get good at soldering. And then I went to a friend's house who had not a expensive iron, like in the grand scheme of things, like an $80 iron, which is, relatively expensive for a hobbyist. And I was like, oh, I'm not bad at soldering. I just have been using crap irons for years. And you can get a decent iron for like $35. I should have linked it somewhere here, but on my website, on my blog, I did a huge post back in February. No, it must have been like Thanksgiving time, about all the tools that I recommend if you're setting up a new electronics workbench. Like, what kind of soldering iron would I buy now, given the choice? And like, I'm not made of money. Like, these are all, inexpensive options, but this is one of those cases where like spending $15 on a basic iron is worth less than half of spending $35 on a pretty decent soldering station. So just get yourself a good, decent iron with a temperature control. Palmer points out you can get ones that have a heat gun and rework station, so it's a little station that will blow hot air for melting solder. Can be really useful. I don't find myself using those tools all that much, but if you're doing a lot of sort of larger assembly, especially if you're using heat shrink, like heat-sensitive wrapping that shrinks itself onto components when you have hot air on it, that can be a really handy tool. And again, like, none of these things, 30, 40, 50, 60 bucks tops, it's a totally worthwhile investment. So other soldering tips as I get to move on with soldering this thing, so we're not stuck staring at a little circuit board all night. The basic technique, and I think most of you have done this before, is you take your hot iron, you hold it to the junction of your two parts, you let it heat up for just a moment, and then you press your solder into the joint. You want to avoid pressing your solder directly into the iron, because then your solder is going to tend to stick to the hottest thing in its vicinity, and if you press it directly onto the iron, it's going to tend to stay on the iron. Other I was going to say pro tips, they're just tips. Once you have used your iron, you'll want to clean it. There's a couple of ways you can do this. Your soldering station will probably come with a little sponge that fits down in a little stand right here. Mine disintegrated about 3 months ago, so I've been using this wet paper towel ever since, and that works pretty much fine. I also have some of this little brass wool you can see hiding down in there. That's really good for if you have solder that's collecting on your tip. You just pounce it in that brass bowl, and that sort of cleans the excess off it, and then you can wipe it on your wetted surface here, and that steam will help really clean it to a really a really clean level. Things that I don't like, and this is a kind of controversial opinion, a lot of people swear by like the tip tinner and cleaner you can get in little circular packets that cleans your tip and puts some solder on it to clean it. I find that they either tin my tip way more than I want to, or they start to corrode my tips over time. There's a really strong acid that's present in those tip cleaners to really get them nice and clean and strong. And if you have a really gunky tip and you leave your iron burning overnight sometime, that's a really helpful tool. But for general cleaning, I find the brass wool and a wet surface is plenty. If the tipped cleaner works for you, by all means use it. Some people find it really a thing they use every time they're cleaning their tip. I just think it's overkill, but that's just me. So I'll zoom back in there. Look at this other solder joint. So you can see I soldered this little point down here. Let's solder the other end of our resistor once we put our LED in. So I need to get this resistor point to this LED and then to ground. So we'll push that LED in just there. All right, and again, I'm going to reach underneath. I'm going to bend the leads outward just for a second, just so that LED doesn't fall out when I turn over. I can't hardly believe that I was sitting here like in virtual silence all evening. It's so much more fun. I was like, I'm just going to plow right ahead, but it's so much more fun to see everything people are saying. Amazing. Thank you all for being here. I saw Chris said take a drink every time Jeff screws something up. That could be a theme. Jeez. So I'm gonna I see you, Michael. I see you. Now I'm like paranoid. Now I need a little bot that like is in somebody else's house that just like, it's like, have confidence, Jeff. So I'm gonna reach back under here. I'm gonna find my resistor from earlier, and when we do the full soldering demo night, we'll come into an even closer camera view. But I'm going to take those two leads of those two components next to each other and just bend them toward each other. So they're really strongly overlapping there. And then I'm going to get in there with my soldering iron. And when I'm soldering, I'm not only going to solder the leads of them together, but I'm going to solder the little metal pads that they're resting on too. And that's going to make sure that not only are those components connected to each other, but they're in a really stable, locked-in position with relation to the perf board. And that'll just make sure that nothing's flopping about where it shouldn't be. Worth keeping an eye on these little nubbins, these little legs that you cut off of components. They're small and electrically conductive, so when you're cutting one off, make sure you know where it goes. If it lands somewhere you don't want it to and short something, that can be a real big problem. Chris points out that a ventilation fan is a really good idea. Yes, fumes from soldering are fairly toxic. The more toxic part actually to insulation is not the lead or other metals that are in the solder, but the flux that is present in the core of a rosin core solder, and almost all of them are. That is the little chemical component that when it gets hot, it actually cleans the surface of your two metals briefly, that allows your liquid metal that you're pushing in there to make a really good contact and stick to whatever metal you're soldering to. The fumes from solder are not particularly great to breathe. I do have, if I zoom all the way out to my messy workstation here, I do have this big chonker of a soldering fan, but this has like a 60 watt 120 volt fan in it that I took off of a musical that was closing, and I think it is too unacceptably loud for trying to talk on mic. So I do not have a fan. Chris makes a good point. Ventilation is key. So now I'm just going to solder the other side of my LED here, and hopefully I haven't screwed anything up. I guess we'll find out. I mean, I guess that could sort of be the theme of not only tonight but every night. I hope I haven't screwed up, because it might take longer to fix than we want, and then it just won't work at all tonight, and that would be really sad. Oh, I should also say, really useful tools for working with perfboard are flush cutters. So as opposed to using like a pair of diagonal cutting pliers, something like this, which has a flush edge, you can really right up close flush to that board before you trim it, is really useful. They sell packs of these Heiko ones on Amazon for almost nothing, or singles for like $4. Really worthwhile investment. So now that's soldered in place, hopefully this works. It might catch on fire. I don't know. I'm always a little nervous about doing these things live, but like I guess that's part of the joy of it. So I could power this off of the 5-volt and ground ports on my Arduino, but just for the sake of convenience, I'm going to use my bench power supply that I've got here. Actually, I should probably make sure it's set to 5 volts before I actually plug it in and turn it on. Palmer says, my soldering vent fan just pulls smoke through a loose weave filter, but keeps most of it from going directly on my nose. Yeah, it's true. Yeah, a lot of them are this hood style. I will say the best solder fan that I have found is actually the Heiko branded one. It's just really expensive. It's like $170 for a fan and a box with a filter, and I can't justify it. So one thing you could do, and actually I should do a post on this at some point, is buy one of these cheapy, this is an AOYE branded one. You can't see. There it is. AOYE branded one from Amazon. It was like $20, and then I put like another $7 fan in it to really boost the juice, as it were. And if I turn it on, I think you'll be able to hear. It really gets ripping. You can probably hear that in the background. I think it's too much, so I'm going to turn that off for now. Even just having like a little fan off to the side somewhere, just gently blowing across your work surface can be nice, just so you're not like breathing in those fumes all day, every day. All right. Tangent. Power supply is set to 5 volts. Hopefully, when I plug this in, hey, there we go. So that's that same blink code that was running a moment ago on the breadboard. So this pin down here, digital pin 9, pin PB1 or whatever it was, is turning on and off once a second. That's letting current go through the resistor, through the LED to ground, and blinking our circuit. So if this, let's tie it all together. Let's say this is what you needed. Let's say you needed to implement the world's most boring version of Tinkerbell in your production of Peter Pan, and you were going to represent her by a little green LED that blunk once per second. You could build that with a full-size Arduino, and an LED, and kind of hot glue it all in place, and it would be a big old mess. But you could just as easily shrink that way down by having your external chip that you now know how to program using the Arduino ISP program, a crystal, a couple of resistors, and LED, and you could strap a little tiny battery pack under there, and that would be not only a much more compact solution, but now a much more permanent one, because all of this is now soldered in place in a way that it's not going anywhere. With a little bit of glue and maybe a little protection on this chip, you could put this on an actor and it would be fine. Chris, I love having you here this evening, because so often I feel like you're asking the good questions of like, what could you do this? And it's the next thing we're going to get to, which I love. You absolutely can go to a smaller ATMEGA for something like this, because as we said earlier, this ATMEGA, no, Chris, you're spot on. This ATMEGA has 32 kilobytes of code space available to it. And if we can actually see how much code space we're using, if we come over to, let's leave that blink in there because I feel so good about it working the first time. If we come over to our Arduino IDE here, from the last time when we uploaded this blink code to the Arduino, I'm going to scroll back, and this will show you a similar thing whether you're in that basic upload mode or the verbose mode. I'm just going to scroll back up through our data here. Here, it tells me it wrote 940 bytes of memory to my flash to run this program. So of the 32 kilobytes I have available to run this program, it wrote wrote less than 1 kilobyte. So definitely overkill. Let's see. I think it actually probably saying considerable less than that. It might be re-uploading the bootloader. Oh, here we go. Sketch is 940 bytes used. Maximum is 32,000 bytes. So we have plenty of room for this program. It's way overkill for what we're doing. Chris says, couldn't we just have used a 555 timer chip to make an LED flash? Sure. If your program brief from your director in your production of Tinkerbell is make the LED flash once per second, there are even simpler and cheaper ways to do it. And this is maybe all coming from, for those, many of you know, I come from a theater lighting background. If a director told me that the light had to flash once per second, I wouldn't be sure it needed to flash any slower than 20 times a second, or as faster than once every 10 seconds. Maybe it wants to blink twice. The advantage of having a microcontroller, of course, is because it's reprogrammable. Let's say it wants to blink once a second, but it wants to be on for a quarter of a second and off for 3/4 of a second, or something like that. Just having a cheap microcontroller, and when this chip is a couple bucks, you really aren't spending that much more to get a lot more flexibility. And if, as Chris suggests, you go down to an even smaller ATMEGA chip or an ATTINY chip, you can get even cheaper than that. So before we carry too far along, let me make sure this is actually the next thing I wanted to talk about. It's the thing I'm excited to talk about. Oh yeah, we're a little out of order, but I think that'll be okay, because we'll circle back to another topic when it makes a little bit more sense after we've looked at the other chips. So let's talk about other chips. We also need to make the LED. Chris says we make the LED sick, where it's a really bad production. I wish I had video of this. I think the reason I pulled Tinkerbell out of my bum for this example is that I have now made Tinkerbells 3 times in my career for various productions. Once at Looking Glass, once at Shakes. Maybe it's just twice. Maybe just 2 sets of Tinkerbells. But both of them had various types of green LEDs that had to flash and flicker and do all kinds of stuff. Peter Pan is kind of the theatrical electrician's nightmare, playground, depends how you're looking at it. But if you have a character who's represented entirely by versions of little tiny lights, having the ability to program small devices to flash in specific ways can be a really good key. Palmer says his stream rewound 30 minutes ago. We're all doing great tonight. Let's be real. We are all doing great tonight. We are hanging in there. We are washing our hands. We are keeping people safe. We are doing what we can. So we're all doing just fine. We will get through. Cheers. All right. I feel like I threw the segue away for the sake of the Tinkerbell story, but that's probably fine. There's no segue deficiency in these Sunday nights, so I think I'll forgive myself. But let's talk about smaller chips. So the ATMEGA 8 family, of which the 328 that we're playing with here is one, has various other members, including here. Let me pull up. Let me pull up the data sheet. I'm going to try not to get too deep into the weeds on reading these data sheets tonight because, honestly, I think it's not really valuable for me to read a data sheet to you over the internet when you could look at them yourself. But I do want to teach people to fish as opposed to giving them digital fish. So give you ways to find information rather than me just feeding it to you. So if I look up ATMEGA 328P data sheet here, I'll go to the DigiKey page. That's our chip that we've been playing with. Come down to data sheet and open that up. we can see that this datasheet is actually shared by multiple different devices when it loads here. This is the datasheet for our friend, the 32.8 and its P variant, the 16.8, the 8.8, and the 4.8. And I happen to know, you could read through, the 662 pages of this datasheet and find a few ways in which they are different, but the primary one, as it notes right up at the top, is that they will have either 4, 8, 16, or 32 kilobits of programmable flash, 256 or 512 or 1K bytes of EEPROM. EEPROM is a more permanent method of storing information on your Arduino chip itself, on your ATMEGA. So as we've programmed things before, as we've used variables and things, we've sort of taken for granted the fact that when you restart your code, when you re-upload new code, those variables are all going to get reset, essentially. They're never going to persist between runs of your program. But EEPROM is essentially like the memory in a flash drive, in that it persists from time to time. So if you need to have a configuration value, say, that is set at program time, maybe modified later, and then is persistent even if the Arduino gets turned off or reset, you can store that information in the EEPROM, and it will still be there the next time you run the code. A sort of classical example is clock calibration, or say musical tone calibration. Let's say, and I'm not recommending this as a good idea, but let's say you are making a bit of code that was like a little player piano that played little doodly-doo tones using the tone function that we looked at back in week 2. The Arduino's timing might be a little bit off, so your middle A might be closer to an A sharp. You might need to have a calibration routine where you could, sort of tune your Arduino with like a piano tuner would to find exactly how much to speed up or slow things down to get right in that tuning range. And then you'd want to remember that value even when the Arduino was sort of reset or recycled, because it would be permanent time after time. You'd want to store that information in the EEPROM so it was usable again and again. You can do basic storage of if you wanted to like make a temperature sensor that stored a temperature reading every hour, let's say, you could store like 20 days worth of single byte readings in your EEPROM before they started to sort of roll over and go back to the beginning, and you could steal them from there later. Of course, you could hook the Arduino up to bigger storage devices, RAM or ROM or SD cards or things if you're doing a lot of data storage, but for storing a few permanent values, a serial number associated with your chip, you can store those in the EEPROM as well. And before Chris falls asleep from data sheets on stream, one of the other differences between the chips in the 8 family is how much SRAM the chips have, and that's the space where your variables are stored, things that might change during execution. So anytime we declare an int, a byte, a char, a string, it's being stored at a specific location in the SRAM of the chip. And those really, I think, are the only differences between the different members of the ATMEGA 8 family. So in our case, right, we definitely don't need 4K of storage to run that little Blink program. We could use what does the 4 series have? It has 4K of storage and still has 512 bytes of SRAM. Piece of cake. We can just buy that chip, usually slap it in place, program it just the same way, and it will work just fine. There may be some slight differences, and we'll see how differences affect chips in the programming bit of this in just a second here. But in terms of their functionality, their code, their pin connections, where the analog and digital pins are, they're generally going to be exactly the same, with these small, like how much RAM, how much flash, how much EEPROM is in them differences. So you can always, that's one way to scale down, is just to a smaller member of the same family. Another way to change things up would be to go to a different family of microcontrollers entirely. For example, let's take another one that I have here on the table tonight, which is the ATTINY 4 series. So this is we're going to take a look at the ATTINY 44A, which is the middle member of the 4 series. So there's a 2-4, a 4-4, and an 8-4. And similarly to the Mega, they all are 14-pin chips. They all function very similarly, but they have slightly different parameters. In fact, let's find out what those parameters are. ATTINY 44A datasheet. Go to the Microchip website. Oh, here we go. Here's our datasheet. So this is the datasheet for the 2-4, the 4-4, and the 8-4. And the fact that they all share a datasheet is a really good clue that they're all going to function essentially the same way. So looks like we could have 2, 4, or 8 kilobytes of programmable flash, 128, 256, or 512 bytes of EEPROM, and 128, 256, or 512 bytes of SRAM. So again, for the code that we're writing, this will probably, for this Blink code that I'm going to keep using as our example, this middle version with 4K of system memory and 256 bytes each of EEPROM and SRAM, totally, that should be plenty of things. For the simple code that we're going to use. So this is now, we're sort of deviating a little bit here. We're not going to use the exact same chip that is present on the Arduino. We're going to use one of these smaller, different microcontrollers. We need to do a little bit of setup work in the Arduino IDE to allow us to program one of these other chips. And essentially, we need to teach the programmer not only a couple of specific things about how to program this chip, but if we want to continue using the language of Arduino to talk about the connections on this chip, we have to teach the Arduino IDE what we mean when we say digital pin 3 on this chip, because it looks totally different from the 32.8 we've been playing with. What do we mean? Is there, and when we say A1 or A2, are there more than one analog chip, A1, A2? Maybe there isn't an analog pin 5 on this chip. So we need a little bit of way of teaching our programming environment when we say digital pin 4, what does that mean for this chip? And here is how we do that. So, let's real quick look at how we make the connections to this chip. I told you our work earlier would sort of presage what we were doing for smaller chips later in the evening. This information is just ripped straight from that data sheet we were just looking at. I literally screen capped it and dropped it in here. So if you were playing with an arbitrary microprocessor, you could find this information for yourself just by Googling the data sheet, pulling this diagram out. So we're going to have power and ground pins that we'll need to hook up as well. And then we're going to hook up those same 4 pins we were playing with earlier. Reset, MOSI, MISO, and the serial clock. In this datasheet, it's labeled as SCL as opposed to SCK, serial clock, and there is a part of the datasheet in at least all of the ATMEL datasheets that specifically goes through, here's pin 1, it is connected to power. Here's pin 2, it should be connected to a crystal if you've got one, or like what all the pins do. So if you're ever not clear as to like which one is a serial clock, you can look it up in this chart that tells you all the functions of each of the pins. I just looked at this diagram and said, oh, MOSI, MISO, SCK, got it. So let's make those connections on our breadboard. What did should it say ATTINY? Yeah, it should. That's a typo. Drink. You drink when Jeff messes up. See, that slide should have said ATTINY. Oh, and I closed it. It's all going so well. We made it 11 weeks. Nate, I think if you might be new here this week, or had watched some of the previous ones, all went perfectly. All went perfectly for the past 10 weeks. This is the first week everything's gone off the rails. For sure. Definitely. Oh my goodness. All right, so let's make our connections on our board here. So we have our reset, MOSI, MISO, and serial clock connections, and we know which pins those are connected to on our Arduino Uno here that we're still going to use as our programmer. So once again, I've got power and ground flowing to the chip here. I'm going to connect my reset to pin 4, according to my chart, 1, 2, 3, 4. Connect my MOSI pin, which is pin 11 on our Arduino, to pin 7 down here. Connect my MISO pin to pin 8. Nate says I'm still catching up on the previous perfect episodes. All perfect, all flawless. I don't know which one has gone most off the rails. This one feels actually fairly staid by those standards. It's all going, other than thinking I was alone for hours on end, we're doing okay tonight. So I've made my connections here. I've got my reset connected to my pin 4, MOSI, MISO, and SCK, just according to the chart. And like before, these pins on the Arduino side of things are listed at the very beginning of this Arduino ISP sketch that's just in your examples in the IDE. So if you're like, oh, which pins are those? MOSI, MISO, SCK, pins 11, 12, 13. Super good reminder. So that is the physical connection part of the project here. Chris says, side question, can you use the reset and MISO pins at the bottom of the board on the 2x3 pins, assuming you have a jack and cable? You certainly can. We'll get to that in just a little bit. Let's show how we program this chip here. This is the physical connection part done. We've connected to our Arduino to the chip that we're going to be programming, but we need to do that second part, which is teaching the IDE how to what the parts of this chip are, what connections does it have, and what should we call them. And this is the part where the community has done the bulk of the important work. So this is the part where we stop taking things that were released by the official Arduino team and start relying on the work that lots of cool members of the community have done to allow the IDE to program other chips other than this singular one it was designed for. If you have a chip in mind, almost all the time you can find a way to program it by Googling the chip in question and Arduino IDE. In fact, that's how I found this one. I have put links in these slides to the resources for all the chips we'll be using tonight, so you don't have to go and find them for yourselves. But what you'll find is, if it'll allow me to click on that, various members of the community have written various bits of code on our favorite website, GitHub, that we looked at a couple weeks ago, how to navigate GitHub code just a little bit. And they've written basically what are called cores, which are just little snippets of code and text that tell the Arduino IDE, hey, for this particular chip, when I say, what pin D1, D2 means, various ways that it can have an oscillator in it. Does it need a crystal? Can it sort of provide its own clock internally? That sort of thing. Someone just has to write that out, and then we need to download that into our IDE itself. So the Demelis has written a very nice code, a bit of a core for the ATTINY 44A, and again, it's linked in the slide, so you don't have to go hunting for it. So once you've found this, often you will find usage instructions that go along with it, which will include a link to a JSON file. Will this let me? There we go. Oops, I've gone back to the beginning. There we go. The JSON file, this GitHub JSON link is really, it's just a way of linking directly to that file online, because I don't want to point the Arduino IDE at the website with all of its formatting and text and links. I want to point it to directly the file that contains the information of what our various cores are and how they interact. And so by using this .json link, which you'll find usually somewhere in the GitHub, and again, I've linked the ones that we're using tonight, you're going to use this link in the Arduino IDE like so. All I'm going to do is copy and paste that link, that JSON link. I'm going to go into my Arduino IDE. Let's do this in our Blink sketch, although it doesn't really matter. And again, a little hard to see the interface, I apologize, so I'll narrate as I go. If you go into File and Preferences, down at the bottom here, this lower text entry box says Additional Boards Manager URLs. I'm going to paste my JSON file address in there and then hit OK. And once I've done that, the Arduino IDE knows to go, okay, well, I have this information about various general sort of standard Arduino boards, but if you put a link in there to a JSON file, it will also reach out to that address and use that as a resource to generate what boards it knows about. And once you've loaded that up, you can go into your Tools menu, come down to Board, and go into the Boards Manager. And this is going to be a listing of all the boards that the IDE could know about given its internal memory and that link to that JSON file you just included. So we're going to scroll down until we find, usually all the way at the bottom. Yeah, so here's our ATTINY code by David A. Mellis. Boards included, ATTINY 45, 85, 44, 84. Great, that sounds like what I want. You'll come over to this right side here and hit install, and that will download the rest of the information about the boards that link is pointing to make them a part of your system. You also will get a version select. It's very rare that your code will specifically depend on which version of this board file you'll need, so I usually just leave it blank. It'll install the latest one, totally easy. So you'll install that boards file. Right, close that menu, and now when I come up into Tools and select my board, this is normally, you've seen me mess it up before, select the Arduino Uno or Nano or Mini. If you come down to the bottom of that list, and again, I apologize for it being a little hard to see, down at the bottom here are the boards that we have added from our boards manager. So I see here a listing for ATTINY 25, 45, 85 and 24, 44, 84. So I'm going to select 24, 44, 84 there. And now if I use my Arduino IDE and use the program, upload using programmer functionality that we talked about earlier, I can now upload this code appropriately to the chip that I have. So let's make that happen. So first, gotta plug my Arduino as programmer back in. That's a win. That doesn't usually happen. I'm going to come over to my sketch here, and I'm going to either in the tools menu go to, or sorry, in the sketch menu do upload using programmer, or hold shift and click on upload, or hit control shift U, all the same thing. So let's upload this blink sketch to this chip. And while it does so, I realized that I took my resistor earlier. Oh, I've got an error. Why do I have an error? That's good. This is actually a really useful error to see. So let's jump to it. So it's giving me all the error information. If you have the sort of standard upload tabs, like not this verbose mode, you'll still get most of this information. It's telling me AVRD is saying device signature OX1E9207. Every microprocessor species that Atmel and really every developer makes has a few bytes devoted to a microprocessor signature, exactly for telling programs communicating with it, hey, what kind of microprocessor is this? And this program is AVRDude program. Which is the underlying program that uploads code to the Arduino that sort of the programming environment is built on top of, is saying, hey, we read those bits before we uploaded code, and we're seeing it's this 1E9207, but we were expecting to get this other value. You should double check that you've programmed things right. And it turns out I have not programmed things right. Cheers. What I've done is failed to set some options in my upload menu here. So, and again, I'll narrate. Should find a way to zoom in on some of this interface stuff. That would be helpful, huh? Here in my tools menu, when I came down and I selected my board, I selected the option for our ATTINY 24/44/84. But I neglected to, in my tools menu, right underneath that, when I selected that as my board, I got given some new options to select, including right below it, which specific processor I have. And here I can see I've selected ATTINY 24 when I really have a 44. So let's select that option. The other option here is for what kind of clock I want to use. And it's giving me the options internal 1 megahertz, internal 8 megahertz, external 8 megahertz, external 16, and external 20 megahertz. So this tells me I can use the internal oscillation power of this chip to run at 1 or 8 megahertz, or if I hook up a crystal, I could run at 8, 16, or 20 megahertz. Since I'm probably not going to bother putting a crystal on this one, I'm going to run off the internal 8 megahertz processor in this case. So hopefully I've configured everything correctly now. If I again come to hold down shift and click on upload using programmer, we'll see it's giving me all the information. It's writing successfully. That's very encouraging. It looks like I have successfully flashed that chip. So now I come back to my table and I'll need to hook up an LED. But the question is, to which pin do I hook it up? How do I know which pin is pin 9 on this thing? If we come back to our diagram that I ripped from the datasheet there, we'll see that everything has, if we go back to the proper slide, everything has these sort of internal names from the datasheet. PA1, PA0, PB1, PB2. How do we know which one is digital pin 9 in Arduino speak? That is relatively easy to determine, I hope, from the GitHub where we found this core to begin with. So if I go to that link, and I swear we'll zoom in when we get there so we can all play along together. If we come into, now some of these cores, and I think the next one just has really nice internal documentation that makes it really easy to find out. What I'm going to do is come into the variants folder here, come into probably in Tiny 8. I'll come into this pins.arduino file. And we'll see. So this is for the ATTINY 45. That's not what I want. This is an 8-pin device. So it must be this ATTINY 14 folder. It's interesting because there's not a 14 variant. But if I click on that folder, I've again got a pins.h file. I'll scroll down here and we'll see they've documented for us. Here we go. A little ASCII art drawing of the chip that we're working with tonight. And we'll see that pin D9, and I could have picked any of our pins, but pin D9 is going to be pin 1, 2, 3 on our chip here. So let's hook an LED up to pin 3, which is digital pin 9, and see if it blinks. Hopefully it does. Everything's gone so smoothly for the rest of tonight. I don't see why this wouldn't work. Let's see here. Pull an LED out of our bag. Let's use a little tiny green LED. That'll be fun. Tiny chip, tiny LED. So I'm going to unplug, just for good measure, I'm going to unplug power while I wire. That's always good practice, is not to wire hot, because you never know when your hand's going to slip and something's going to go wrong. hook up that LED to pin 1, 2, 3 there, and then we'll need a resistor of the appropriate size. From our previous experiments in Ohm's law in week 5, he said, kind of guessing, we know that a 220 ohm resistor would be just about right. Chris says it's a good idea as long as I hook up power. Yeah, that is also, I mean, that is maybe the most common failure on these these Sunday nights. It's just, why doesn't it work? Oh, you haven't turned the power back on. But I'll put a 1K resistor there just to be a little bit overkill. Hook the power back on. And as soon as power is applied, we can see the LED blinks. Hey, that's exciting. We're 2 for 2 on blinking the first time. It's the little victories that I will celebrate on these Sunday nights. Ooh, I'm going to celebrate remembering to turn my soldering iron off. That's a victory in and of itself. So now, again, we have blink code running on this smaller chip that is written in exactly the same language that we wrote our sort of general Arduino code in. And I guess this is kind of, this is a point we haven't touched on yet, is when you're programming something like, where's our 328? When you're programming the 328 chip, you are essentially programming an Arduino. You know, the microprocessor is the same, the abilities are the same, the capabilities are the same, the code is the same. There's nothing you have to worry about. As you step down into smaller chips, you will sometimes get reduced functionality. It's all in the various data sheets, but the kinds of limitations that you're likely to run into are, I mean, the obvious one is number of connections, right? This has many, many points of digital and some analog connection points and some pulse width modulation points, which is great for many projects. Part of the reason we scaled down to this, and we'll continue to scale down into even smaller chips, is we didn't need all those points of connection. So, but if you were doing a project like communicating with a very large LCD that also had several switches and buttons and LEDs, you might be yearning for a chip that has more points of connections on it. You similarly might have a limited number of either analog input or pulse width modulation output connections. Let's see, just out of curiosity, I think this one specifies, yeah, so our friend is it David, has helpfully drawn out for us here that the ATTINY 84 has 1, 2, 3, 4 pulse width modulation pins as opposed to the 6 on the 32/8 pin. So again, it's about quantity of connections that you need. You also, of course, have less program space, and because I'm running this at an 8 megahertz clock speed as opposed to a 16 megahertz clock speed, I'm, of course, executing things twice as slowly. Palmer asked a good question, which is the different clock speed in the crystal doesn't affect the sort of time in the code. It doesn't affect things like millis or delay or microseconds, micros, which is the analog of millis, but for microseconds. The differences in clock speed are accounted for in the ways that those various functions are written in the code. So no, delay 1000 is always waiting 1000 microseconds. Whether you're running at 1 megahertz or 16 megahertz, it's taken care of in the background for you. It does mean, though, that like your code will be running at slightly different speed, which, if you're doing a lot, can make a big difference. To draw an example, a couple weeks ago, for those of you who were here, what night? Oh, it was the infrared remote controls night. We had Hunt for Red October going on the TV in the background as our infrared remote control target. When we were closed for that night, I did a bit of playing around using an Arduino variant to generate composite video to shove pixels into that TV directly, which is kind of a cool project. But if you imagine, so that's generating black and white data for thousands of pixels and trying to do it as fast as possible. It makes a big difference if you're able to run 16 million fundamental operations a second, or 8 million, or 1 million. I really, even running at 80 million, and this was a slightly bigger processor that could do a faster bit of operation, even running at 80 million fundamental operations per second at 80 megahertz, I was only able to get 5 or 6 frames of video per second out of the thing, just because of how much data I was needing to process to get each of those frames out. So Palmer, in answer to your question, like millis and delay and sort of basic time things are all calibrated for you, but of course your code itself, you're not going to be able to run as many lines of code as fast because your clock is moving slower. Does that make sense? I think it makes sense. Other things, other differences between chips as we move on to our last couple even smaller chips tonight. The reason that you get let's say, 6 pulse width modulation outputs on the 328, or 4 on the 44A, or I think 2 on the 85A that we'll look at in a second here, has to do with some internal hardware that is built into the chips. Specifically, a bit of hardware called a timer, which essentially is what it sounds like. It is a value, it is a variable that's stored internally that counts up, typically by 1 every clock cycle, although there is some configuration to say, hey, only click up by 1 every 2 clock cycles, or every 4, or by 16. And sort of, you divide the clock cycle by a set amount before you figure out how fast that clock will increment. And to do pulse width modulation, what's actually happening under the hood, so to speak, is that you are setting a timer inside of, say, this chip, the 328, to count up at a certain speed, and when it reaches a set value, to turn a pin on or off. And you might change what that value is based on, you know, the how long you want your pulse to be high for and how long you want your pulse to be off for. And because only certain external connections are hooked up to the timers to be able to do that, that's why the PWM outputs are only in specific pins of your Arduino. In a similar way, there are specific pins on, say, the 44A that are hooked up to specific timers inside the chip, but this chip only has 2 timers, whereas this chip has 3. And I believe these only have 1 primary sort of general use timer here. Those timers are not just used for things like pulse width modulation, but we've alluded to before, those timers sometimes get reused by other libraries, like the library that writes to NeoPixels, or WS2812, the sort of individually controllable LEDs. That makes use of, I think, the stock library Timer1. So if you're using that library, you can't use 2 of your pulse width modulation pins on your 328, because they're taken up by that library. That timer's just doing something else. In a similar way, you could probably run that code on something smaller, but now instead of having 4 out of 6 pulse width modulation pins, you might have 2 out of 4, or have 0 available, or something like that. So as you start to like really get into stretching what the small chips can do, you can run into not only limitations on sort of the default functions of these pins, but the fact that under the hood, some libraries and some additional functions might make use of that underlying hardware in a specific way that might limit you a little bit more than if you're using a bigger chip. That's a kind of a rambling explanation of the limitations here, but hopefully it makes sense. One thing I don't think I mentioned working with these chips is, and I think I forgot because I did it earlier today, when you're programming a new, smaller ATMEGA or ATTINY, just like with the sort of a full-size one, for lack of a better word, the first thing you should do is burn a bootloader. And it works exactly the same way as when you're programming the 328. Once you've selected your appropriate variant from your tools menu here, you come down to the bottom and hit Burn Bootloader. And this is not so much to give you the capability to program this like an Arduino over a serial line. These chips are just not really configured to do that. But like we were talking about earlier, you do want to make sure that you set all of those configuration settings appropriately. You want to tell it that it's, hey, you're going to use an 8 megahertz clock or a 16 megahertz clock. It's going to be internal, you're not going to use a crystal, and so on. And doing the burn bootloader function in the IDE accomplishes that. If you don't do that, you can typically still upload code, but it won't run, either it won't run at all or it won't run at the right speed. And in fact, the first time I plugged this one in and I ran this like blink on and off once a second sketch, it was blinking on and off once every 8 seconds. It was like on for 8 seconds, off for 8 seconds. And that was a clue to me because I knew that 1 megahertz and 8 megahertz were the viable clock speeds. So I was like, wow, something is strange here. I forgot to load the bootloader. So it's running what it thinks is an 8 megahertz program on a 1 megahertz clock. So everything is running 8 times as long. If you just burn the bootloader, everything will be just fine. If you change the clock speed, though, like let's say I wanted to, instead of running this at 8 megahertz, run it at 1 megahertz for some reason, I'd want to re-burn the bootloader to set those configuration settings correctly. The technical term, I should say, for those configuration settings is fuses. it's based on old programming necessities of how you would have to set those settings in older chips. But if you hear someone saying burn the correct fuses or burn the clock fuses, that's what they're talking about. It's all wrapped up in the burn bootloader function in the IDE, but those configuration settings, because we haven't mentioned it, are called fuses for our purpose. Let's blow through 2 more tiny chips, and we'll see how long that takes us, and then we'll get to Chris's earlier question about the 2x3 connector on the Arduino. So just to drive home the point of how this all works, let's look at a couple more chips. Let's come down. Actually, I think you'll believe me when I say that these chips work in a similar way. So we don't need to do necessarily both of them. Let's just do the smallest one of this, which is the ATTINY 13. This is a little itty bitty guy. It's an 8-pin chip. It's this little guy down here. It's less than ½ an inch on each side. It only has 8 pins, and 2 of them are taken up by power and ground. So let's get that working in our IDE. Much like before, I'm going to need to take this JSON address and load it into our IDE. And I would think MCU Dude has written a lot of these, and he has has a really great bit of documentation. Tells you how to install it, what the settings are, how to use programmers. Really great example. He actually lists this JSON URL in his documentation here, which is super convenient. So just like before, I'm going to come up into File, Preferences. In my Additional Boards Manager URL, I'm going to paste that JSON address. I'm going to come to my Tools menu, and under Board, I'm going to go to my Boards Manager, scroll all the way down, and I found this Microcore by MCU Dude. Supports the ATTINY 13. That's what we want. I'll install it if I haven't already. Close that up. And then in my Tools menu, when I say what board do I have, I can scroll all the way down, and I have an ATTINY 13 option. Let's double check that I have my options set correctly. Oh, there's a couple of new ones here. And man, this interface where you can't see the menus is not ideal. I'll just narrate in my sumptuous narration voice. Hang on, let me nurse the narration voice. So, the options, dear reader. No, I'm not going to do that. So I've selected my board, the ATTINY 13. The next option says BOD, which is brownout detection. You can have the microprocessor, at least the ATTINY 13, you can say, hey, you're a 5-volt part, but it can run down to, I want to say, 1.8 volts. It's a pretty flexible part in that way. You can run it off of a variety of voltages. But you can say, hey, if your supply voltage dips below a certain level, I actually don't want you to keep running. I want you to just shut down. Let's say the rest of the parts in my system are only 5-volt parts that'll turn off anyway. So if my part dips below 4.5 volts, say, I'd rather this microprocessor just shut itself down until the power comes back up. So I have 4 options here: BOD 2.7, 4.3, 1.8, and BOD disabled. And those are the various levels that you can say, hey, if the voltage falls below this, shut yourself down until the voltage comes back up. I'm going to set BOD to 4.3 since I'm going to run this off of 5 volts. It gives me a clock option. I have lots of clock options. I'm just like the fastest internal oscillator that I have, which is 9.6 megahertz, just so I don't have to bother connecting a crystal to it. I have a timing option here, which says micros disabled or micros enabled. And this refers to the micros function, which is the analog of the millis function, tells you how many microseconds have elapsed since the start of the code running. That timer, that internal bit of hardware that's responsible for maintaining that, takes some significant chunk of power compared to the rest of the chip to run. So it basically gives you an option in the programming here whether you want to enable or disable that timer just to save that bit of power. So I'm going to leave micros disabled since I don't need it for this blank sketch. Millis will work just fine. Micros you have to explicitly enable. I'm on port 11 as usual, and that should be all we need to do. Now, of course, I can't use pin 9 for my blink sketch here since I only have 8 pins on my chip. So let's go back to MCU Dude, and again, linked in the slides so you can check this out for yourself. I'm pretty sure he has a really nice drawing of which pins are assigned to which digital values. Yeah, look at that. That's classy. Look at that. Beautiful. Oh, so good. So let's pick a pin. Let's do digital pin 0 down here. We're going to make our blink one. So come back to our blink demo. We'll say pin 0. And we'll just blink on and off once a second as before. So again, I'm going to hold Shift and click on the upload button. That'll upload using my programmer. Oh, it would help if I... Hang on. You gotta hook it up first. Gotta hook up the darn thing. All right, so unplug that. We'll leave power and ground connected, and I'll take a quick peek in our slides at the various connection points. So just like before, we have our reset pin, MOSI, MISO, and serial clock. So our reset pin from pin 10 on our Arduino is pin 1. Our MOSI pin goes from our Uno pin 11. MISO is from pin 12 to pin 6, and serial clock is pin 7. So, yeah, you can drink for... Yeah, listen, we goof up a lot of things, but forgetting to plug the darn thing in, that's an exciting time. All right, so that is now hooked up. That's very good. I will now plug the Arduino back in. I'm going to steal this LED for a second for later. In fact, let's just plug the LED in now and see what happens. So one thing you might notice is I am now, because there are so few pins on this ATTINY 13, I'm going to be plugging this LED into the same port, the same pin that my programming wire, my MOSI wire, is connected to. So is this a problem? It depends what this load is. Because when we're programming this chip, this Arduino needs to be able to successfully drive this pin high and low, 1 and 0, to communicate data to the chip. As long as the load on that pin is sort of small enough that it's not preventing that pin from going all the way high, or I guess conversely all the way low, programming it with an LED attached is fine. Since I've got a 1K resistor here plus an LED, I don't think, even if we put 5 volts on this line here, that pin is probably going to be, you know, at 4.2, 4.3 volts. I'm not super worried. But you wouldn't want to have, say, a much lower impedance load, something that's going to really drag this pin down, because otherwise we won't be able to program it with this attached. Now, I might be eating my words here in a second. This might fail. But if it does, then we'll all have learned something together. So we'll come back to Arduino IDE now that we've remembered to actually plug things in. We'll hold down Shift and click Upload. And we'll see what happens. Oop, I think it happened. That was fast. And it tells us that we're only using 86 bytes of flash memory of the, I believe, 1K of flash that we have in the ATTINY 13. Let's just verify that before we see the successful results. Spoilers. It worked. It's running. How exciting. So now we have this little tiny chip running this little tiny LED just to make a blink. That's very good. Let's just, for curiosity's sake, let's see how much space we have to work with here. Although I guess it'll tell us in the IDE. It'll tell us I'm running, right? Oh, it'll tell us when it compiled. We'll go all the way back up here. Yes, it says we're using 86 bytes. Maximum is 1,024 bytes. So, on the one hand, this is great. This program takes almost no code space to run. On the other hand, it's already using 8% of our code space just to run this blink sketch. Really starts to drive home like how small the program space is on these things. If we night another one of our favorite examples, like a breathing LED, let's just say let's see how much space that takes. Int I equals 0, I is less than 256, I plus plus, analog write pin I, delay 10. In fact, we won't even do a breathing LED. We'll just have it fade up and then snap back to 0 and fade up again. So again, I'll hold Shift and upload. It'll compile. It'll upload. And we're done. So that, which, let's see if that worked. I actually got a little lucky here because it seems we do have analog output on this pin, which I didn't bother to verify in the data sheet before it happened. But hey, luck is good. I'll take all the luck I can get. So now I have a little fading LED on that little tiny chip. But if we look here, we'll see I'm now taking up 13% of program storage just to do this little breathing LED. And if I copy and paste, we'll do a fade down. Let's say we start at 255. I is greater than or equal to 0, I minus minus, and we'll upload that using the programmer. Uploaded. Now we have our breathing LED. That takes 25%, 256 bytes of program storage space. Now it looks very nice. Like, look at that. If you remove the programming wire, would the LED be brighter? Good question. Let's find out. I need to do a little, to reset my stream controller here real quick, but as I do, you can click over here. The answer, I think, and I guess I'll find out, is no, because once we're done programming, the programmer goes into a state where it's not affecting anything in your circuit anymore, goes into a higher impedance state, so it shouldn't be loading anything down. So if I plug and unplug this wire, we shouldn't see any major difference. I'll shield that so we can see it a little bit better. Yeah, if I plug and unplug that, shouldn't be seeing any noticeable difference here. And that's the programmer just doing its job and going into that high impedance state, saying, I'm not going to affect anything once we're done here. Should be drawing no power, should be supplying no power. I will say, I definitely got lucky that pin I happened to choose faded. That worked out very well. If you were doing your due diligence, you might, hang on, we can do this better. Come back over to the computer. If you were to look at, say, there we go, the very nice pinout that's linked in the GitHub link there. This person's very nicely drawn out all the various connections. We can see this pin, its proper internal name is PB0. You can use it for interrupts, which we haven't talked about yet, interrupt 0. You're going to call it digital pin 0, that's our MOSI pin, and it's OC0A, which if we look over to our notation here tells us that's a timer/PWM pin. So we get 2 PWM pins here on pins 5 and 6. We get 4 analog to digital converters, that's our analog read pins. We get a serial interface. We get all kinds of interesting things in this chip. For a chip that, this chip costs, I think, 80 cents if you buy just one of them, and it goes down in price in there if you buy bulk. It's really quite crazy, and it's so tiny. It's so adorable. Like, you know, if you were making, say, I don't know, a herd of fireflies that you wanted to just, you know, wait until it was dark, say with a photosensor, and then, you know, flash on once every 5 seconds. Using something like this, a little tiny chip, drawing a little bit of power with maybe a battery or a solar cell and a little tiny LED would be a perfect way to do it, and then you're not stuck faffing around with what, honestly, now that we've been staring at this little one, this feels massive, let alone something like this. So using a smaller form factor chip like this can save you in size and complexity as long as you don't really need anything bigger or the capacities that are or faster depending on your clock speed or something like that. Palmer says, will the dot on the chip always indicate pin 1? Yes, the dot always indicates pin 1, and if you have a chip that doesn't have a dot, and in fact I noticed that this 44 I don't think has a dot. It actually has a little, I have to figure out how to show this. I think my camera is not set up the best. Maybe this camera will be better for this. I don't think I can get it to focus that close. My lighting's just not set up to focus super tight on this guy. But this one doesn't have a little imprinted dot. It has a silk screened triangle. Really hard to see there, I'm so sorry. But it does have this physical notch. If you have a chip with a notch, pin 1 will always, this pin 1 will always be on the left of the notch, so to speak. So if this is the, let's say the top of the chip, pin 1 is always in the top left. And as we talked about a bunch of weeks ago now, the pin numbers will always run pin 1 in the top left, run down, increasing all the way down, then jump across to the bottom and run up the backside. So for this 14-pin chip, we have 1, 2, 3, 4, 5, 6, 7, jump across, 8, 9, 10, 11, 12, working back up the other side. That'll be indicated in all of the chip diagrams and various things. You know, these ones that I stole from the data sheets, right? We go from 1, 2, 3, 4, 5, 6, 7, 8, and so on, but just a good thing to remember. Mary, my wife, is apologizing if there's rogue dog barking in the background. There is a truck in our neighborhood unloading things, and that is unacceptable. According to our dog Winnie, they must be told that that is wrong. That's pretty good. Where was the dog when you did jet just then? Yeah, maybe I need a little, like, need to train the dog that when she sees, like, a, you know, need a text message service, like text and like a light lights up, and then she's trained to, like, come and bark at the door to tell me that I screwed up the stream. Oh, I love it. I love it so much. But very good. So that is the gist of programming microprocessors, either ones that are identical to the Arduino or other variants. Questions on that? There's a couple more little topics, but what have we hit so far that we have questions on that didn't make sense that we just sort of blew through, if anything? And no questions is fine, but like here's a good window while I hydrate and laugh about how goofy and adorable my dog is as I take a drink. Get trainer to bark when I turn lights on. Chris says datasheets talk about milliamps consumption. Ah, yes, they do somewhat. Datasheets, yeah, so Chris is referring to if you wanted to start turning off parts of the chip, or just like using the chip at its base for how much power it's going to draw. So here's what the datasheets generally will tell you is how much power that they draw in their low power mode, because if you're using it in an active mode, let's say like to drive an LED, in a situation like this where it's flashing an LED on and off, probably the majority of the power that this is drawing is actually going to be the current through the LED. In this case, maybe 5 milliamps max. That's going to be about as much, maybe a little bit more than what this chip is drawing. So typically you may or may not get data on how much it sort of draws by default, but you will get data on how much power it draws in its low power mode. So let's see here if there's any first page data. Yeah, so on the first page of our ATTINY 13 datasheet here, we see low power consumption. Oh, actually, this is interesting. Active mode, like fully running all peripherals on, 190 microamps at 1.8 volts and 1 megahertz. So reducing your operating voltage and lowering your speed both contributes to power savings. And so this is this figure they quote up front, because they assume if you're really being conscious about power savings, you're probably running this at as low a voltage as you can and as slow as you can. So you might say, okay, well, if I'm running it flat out, 0.2 milliamps. If I'm running it in idle mode, which is the bunch of things turn off waiting to be turned back on by something, 24 microamps. Let's see if the AT, I don't know that the 328 does, or the 32.8, but let's see if the ATTINY 13 datasheet will give me power consumption for other modes. We'll just do a quick find and search. Supply current of I/O modules. Yeah, so it's starting to, let's see. Yeah, so here's a little interesting table that I've just stumbled across. Let's just see. So it tells you for various peripheral modules, for timer 0 and the ADC module. So timer 0, remember, is that accessory that's like driving pulse modulation and some other libraries. If you run your ATTINY at 2 volts at 1 megahertz, that module, and let alone anything that's outside being driven by that module, is only going to draw 4 microamps. If we go up to 5 volts at 8 megahertz, that same module draws 115 microamps. Similarly, the ADC, the analog to digital converter, the analog read module, if we run it low and slow, 180 microamps. If we're at 5 volts and 8 megahertz, almost half a milliamp. So depending on, there's a whole section in this data sheet if you want to dig into it about like how things are power budgeted out. But idle current, 30 microamps, 40 microamps, but as you start using more and more of these peripherals, getting up into the milliamps range with everything turned on by default is probably more what you're looking at. Palmer asks, just to confirm, you cannot program a new chip if there isn't already a chip in your Arduino. An Arduino board will not program a new chip on its own. Yes, that is correct. So if you have... if you bought one of these, let's say 32.8s off of DigiKey unprogrammed, you cannot, as far as I know, there is not a way to, I don't believe so, you cannot just plop this into the socket on your Arduino and burn the bootloader onto it. You have to use your existing Arduino to at least burn the bootloader. And then you could pop it into your Arduino and use it as usual. If you're buying these chips from like Amazon, you can actually buy them with the bootloader preloaded. Given how easy this is to do once you have an Arduino, I don't think it's worth it. Like you can buy like, they end up being like $3 or $4 a piece to get them with the bootloader already loaded versus like $1.90 I think from DigiKey. So you've seen how easy it is. I would say burn your own bootloader, but it's out there if that's a useful thing. Chris says, most of the battery power is really about the things that are hooked up and not the chip itself. Yeah, exactly. Now, I guess, that's for any device that has like an output to like light or sound or things like that. If you were, using this chip, going back to like our temperature sensor, like doing a temperature log, wakes up every 10 minutes, takes a temperature measurement, stores it to an SD card, and goes back to sleep. The act of writing it writing that data to an SD card will probably take a little bit of power. The act of like taking the measurement, probably not so much. And then the thing to do, excuse me, would be to put it into a low power state. And like I say, we're not going to get all the way down this rabbit hole tonight. Where you essentially turn off a bunch of those peripherals for a set amount of time, and that saves you a bunch of power while you're just waiting around for the next thing to happen. I took a few notes on this because I thought we might stumble into this topic tonight. This is just like a real base overview. Like I say, we should maybe do a whole night on this because low power stuff is super interesting if you're talking about long form use. But standard mode, everything turns on, and then something like this is I think for the 32.8, but all of the AVRs have a similar functionality. You can take sort of one step down from full functionality, which is called idle mode, which turns off the CPU clock and the flash clock. So we're not running any code, and we're not storing any data, but all the other peripherals are on. So you can still have a pulse modulation running. You can still take in and take out serial data. You can use SPI or I2C, as which are other protocols that chips use to talk to each other. You do basically anything except run your own code. And there's functionality for wake me back up from the idle mode when a byte comes in on the serial port, or when I get a message over I2C, or when this pin goes from low to high, I want you to say, hey, I have a low power module just watching that pin and says, oh, that pin went from low to high. Now is when you start running code again, something like that. So that's a way to sort of basically decrease some power consumption. And then they have this even lower power state, many of them, but the main one is called power down, which turns off timers. So no pulse width modulation, no analog to digital conversion, stops it running off of the external oscillator. So the crystal stops oscillating. And there's a very small number, basically everything internal that could wake it up is shut down except for this one timer that has a very few, pre-configured values that say, hey, wake me up after 1 millisecond, 2 milliseconds, 4, 8, and so on. 1 second, 2 second, 4 second, 8 seconds. It says, shut me all down, but leave this little stopwatch going and wake me up in 8 seconds when I'm going to do something new. And that's how you do some of these like really low power long-term things, is put it into as low a power state as possible, let this little tiny bit of hardware that's sipping microamps just wait to wake it back up, wake up, do a brief burst of a thing, and shut down again. It's how a lot of like Internet of Things sensors work, is like, I have 100 motion sensors in the woods tracking animal movements or whatever. And largely what they're doing is sitting around in idle state, and when something changes, they wake up, they do something, they send something out over their cellular radio, and then they go right back to sleep. And that's how you get a long lifetime out of your battery in one of these devices. Good questions. All good questions. Let's go back briefly to Chris's question about the 2x3 header pins on the Arduino here. And then I want to show you some extra bits of technique and hardware that you can use if you're going to do a lot of these. And I'll tell you, like, the first time I programmed one of these, my first thought was like, wow, this chip is 80 cents. Each of these parts is like 5 cents. If I could get a power source on here, like, this is a little tiny programmable Firefly for $1. Now all of a sudden I'm thinking like, ooh, I could make like 30 of these for the cost of a nice dinner. Like, that's cool. So if this starts to unlock like possibilities in scale, I want to talk to you just a little bit before we go tonight. I see we're coming right up on our target 90 minutes, as always. Show you a couple more bits of hardware and technique you can use to make this a little bit easier on yourself. And in that vein, one of those is the ISP header. So we sort of talked earlier about how the bit of Arduino code, we were using this Arduino as an in-system programmer to use this as a programmer to program other things while they sit in their circuit or in their breadboard or something like that. There is a standardized interface for those 6 connections that we've been making all night: power, ground, reset, serial clock, MOSI, and MISO. Those are like the 6 essential connections you need to program most microcontrollers. And what they've done is broken them all out nicely to this little 6-pin connection header here. So if we look at the pinout of those connectors, and this, I should say, this is a standardized pinout that is not unique to Arduino or Atmel. Really, all major manufacturers have adopted this pinout as more or less standard, at least as far as I can tell. So this is the layout of the 6-pin version of this pin header. the specifics, so pin 1 up here, which will always either be a square pin or be notated on the R3. It's hard to see there, but you get a little white dot next to the pin header. That's there to indicate that that is pin 1 on this header. That will be your MISO pin. Pin 2 is VCC, pin 3 is 0 clock, MOSI, reset, and ground. So all 6 of those connections that you need are broken out right there for you to use. There's also a 10-pin version of this header floating around that has 4 more ground pins. To be honest, I don't know the history of why there are both. I think the 10-pin exists for sort of historical reasons. But given that we have those 6 pins sort of broken out there nicely for us, we can start making use of some additional hardware to program pins using those rather than hooking up our 6 individual wires each time. We might use, oh, now where have I shoved it? Here we go. Something like this. So this is a cheapy cable. This is a 6-pin to 6-pin header cable that I bought off Amazon, I think for less than $5. That is designed to plug into the header, say, on your Arduino or your programmer, and then plug into a 6-pin header on another board to program with. So let's say I was making an experimental board with this little guy, and I was suspecting I would need to reprogram it fairly often. Instead of having to hook up wires individually each time, and if this is on a piece of perf board, hooking up wires each time is kind of a pain, if not really possible, I might build in a little 6-pin header into my project that I could then plug the other end of this cable into. And that header could be pre-wired to the specific ports on my chip that I need to program, and that would make it really easy to plug and unplug to program this Arduino or this chip or this ATTINY or the Mega or whatever I needed to as many times as I needed to. Just useful that all those connections are in the same place. Another thing you might do is, let's say you're now dreaming about, as I often am, as I get into these little tiny chips, I'm like, they're so cheap, and they're pretty versatile. I mean, 1K of code isn't a ton, but it'll flash, it'll blink, it'll do interesting things. What could I do if I had 50 of these? If you're going to be programming 50 of these, let's say, another thing you might make use of is something like this. So this is a circuit board that I've sort of built myself out of a piece of perf board that we talked about earlier. This is what's called a zero insertion force socket, or a ZIF socket. So in contrast to the sockets we were looking at earlier tonight that I plugged that 328 into, which have just little springs on the side, this one has a little lever up the top, and I don't know if you can see. Let's find out. If I move this lever, you can kind of see little plates of metal move and actually squeeze the pins that are in these holes together. So the reason it's called a zero insertion force socket is that if I take a chip like this one, I don't have to push it into the socket. It should just slide down in there. Of course, it would better if the pins weren't bent, but it just slips down in there, right? It sits right in, nothing doing, comes right out, not permanent at all. But when I push this lever down, now that chip is trapped in place and makes really good electrical contact. And this is designed exactly for applications like this, where let's say I have to program 50 of these little guys for my cloud of fireflies that I'm now thinking about. What I would do, and what I had done for a previous project, is wire a little 6-pin header on here, wire it specifically to the 6 places on this chip that need VCC and ground and 0 clock and MOSI and MISO and reset, right? It's all wired up underneath to be wired correctly, right? And then to program it, I would leave this plugged into my Arduino, right? Or my programmer, right? Leave that plugged in. I take a chip out, I pop it in, I close the lever. And the advantage of the lever is I'm not pressing down and yanking pins out. It's really easy to slip in. I lock it in place, I program, pop the lever up, take the thing out, and we're done. Right, and I can repeat that over and over again. So these zero insertion force sockets are kind of handy if you're doing a lot of these. Of course, the relationship of the header to what it's wired to on the socket is going to be dependent on the microcontroller you use. But you can, of course, wire multiple headers into the same socket. So I might say this header is wired into the positions on this socket that correspond to an ATTINY 13. And this header is wired into the positions on this socket that are good for an ATTINY 44, and so on. Now, it would be helpful if you labeled them afterward, Jeff, in the past, but you don't have to buy a separate one of these sockets, because they're a little pricey. I don't know, a few bucks, like $6 or $7 for the cheapy ones, maybe a little bit more. But you can reuse them if you have multiple headers just sort of wired individually. So that's a little pro tip there. And then One other thing I wanted to share is if you were going to be doing a lot of these, if you're using the ATMEGA 328, which a lot of people are like, if you were thinking about like taking this off board, I recommend experimenting with the 328 first, kind of like we did tonight. If for no other reason than your results will be the most predictable if you're familiar with the Arduino, because you can always run the same code on your Arduino and see what happens, and then see if the same thing happens in your circuit board that you've built up, and if they don't match, you have like a working copy to sort of base things off of. So I'd suggest starting there and then stepping down to smaller variants if this is the first time you're playing around with this, or just go wild. Like, just go wild. But if you're doing a lot of 32/8s, you can get something like this. This is a product, I should have linked it. Maybe I will after this video comes down. This is a programming shield. It's the ISP Shield V2 from Evil Mad Scientist Laboratories. And you can see it combines some of the things we've been working with tonight, including the 0 insertion force socket, into a shield form factor that's meant to slot right on top of the Arduino. Let's see if I can get that to slot in. We haven't talked too much about shields, but they come in a variety of uses. If that snaps right in there, it's already making all the connections internal to the circuit board that we would need. So for this, I could just slap my 32/8 into that socket, close it down, program it, pop it out, and I have a 32/8 ready to go. Piece of cake. This would be a really easy way if you needed to burn a bunch of bootloaders onto 32/8s, of course, because this setup is functioning the same way as hardwiring it onto our breadboard. The connections are just already made for us on this nice PCB. This is also, this shield was like $15, so if you're doing a bunch of stuff with the 32/8 specifically, it's a really nice buy. It's really well made. Evil Mad Scientist, they're in my hometown. They're really good folks. They make good LEDs and good products. Not sponsored. I just like them a whole lot. So one last thing, you just to point out that there are products on, you can use your Arduino as your in-circuit programmer. You can also buy standalone programmers that hook up to your computer and have that same ISP header on them because it is standard, that plugs into your board or your breadboard or whatever to program with. This might be a slightly more durable option on your workbench if you were going to do thousands of these rather than having loose wires from your Arduino. Maybe it's nice to have it all encapsulated. Look for ISP programmer. There's a million of them, and they're all pretty much the same. Let's see. A couple of things here. Palmer says, do you ever run into trouble with a scrap of wire getting under your perfboard project? Seems like it would be easy to short something with those. Not terribly. I have had it happen. You mean, so like, Palmer, I think, is referring to like things like this, where I have the wiring underneath and I just throw it down on the table, and is there something underneath shorting it? I haven't run into that a whole lot, but I do also try and keep, this is why I try to really police the conductive scraps from my component legs or stray bits of wire that I've snipped off. As long as there's nothing conductive on your work surface, you don't have to worry about it terribly. Of course, if you're working on a conductive work surface like a metal workbench or a table, then you definitely have to worry about it. So yeah, shorting things out underneath is a real possibility. I don't have it happen to me too often, but that's also because I've chosen to be diligent about the cleanup as I cut, rather than being diligent before I plug it in. Chris says, purpose of the second meso pin setup up by the USB plug. Mine is pins. I don't think yours is currently populated. Oh, Chris, I think you mean the 6 pins that are up in this corner of the R3 here. To be honest, I am not 100% sure, but I think, we can find out together. I think those are the ISP header for the microcontroller that is running, that is doing the USB communication on the Uno, or on the, on the Uno. Let's see if we can figure out if that's true. R3 schematic. Let's find the full image that I stole that screenshot from earlier. Is this big enough? Let's see. Yeah, open image in new tab so we can scroll around in it. So here we go. So here in the schematic is the, let's get bigger, and is the ISP header for the main ATMEGA 328. All right, it's got its 5 volt, it's ground, and it's connected to various places on the reset and MOSI and MISO and stuff. Let's see if we can find the other 6-pin header. Yeah, here we go. So that in itself is an ISP header, sometimes called an ICSP header, in-circuit serial programmer, same thing. That is the ISP header for the ATMEGA 16U2, which is this other microcontroller that's configured to do the USB programming. Let's see. Yours, it's interesting, Chris, yours has pins, mine doesn't. I don't know why that would be. I mean, I'm not looking to reprogram my 16U2 at this point, so I guess I don't need those pins, but it's interesting that yours got populated and mine didn't. I don't really know. You can do interesting things. This is we're way off the bounds now, but you can do interesting things with that 16U2, which is responsible for things like when I plug this into a computer, and I go to my IDE, I come into my board menu, it tells me that on COM port 3, it knows, you can't see that at all, it knows, you can't see that either, that on COM 11, it thinks there is an Arduino or Arduino Uno, and that's because the microcontroller that's handling USB is doing a little bit of identification of itself as an Arduino. It has a little bit of code to do that. You can reprogram that microcontroller to tell it that the computer that it is other things, that it is a generic MIDI controller or a generic SMPTE controller, I think. I'm not sure about SMPTE, but MIDI I have definitely seen done. That's a situation because it is currently set up to basically pass data through from USB to the 328. If you wanted to do any programming of that microcontroller, you would need to use that ICSP header that's, at least on my board, not populated here. I wonder if any of them have it pop. Oh yeah, so interestingly, so here's an Arduino Mega, which is in many ways designed to share the first half of its form factor, and then they've bolted extra stuff onto it. On this one, the ICSP header is populated. So that's kind of interesting. It's similarly, does it have, yeah, so that's its little ATMEGA 16U2. That's doing the USB communication, and they've left the programming pins on there, or it's installed them in the first place. Yeah, I don't know why that is. Maybe it's differences in branding or manufacturing, maybe to save like a couple cents on each unit. It could certainly be. Have we talked about all the things? Have we suddenly come to the end? I think so. Let's check the slides, but I think we've talked about all the things. This is a good time for questions as I'm trying to figure out what the heck is happening. Let's see. We talked about low power. We talked about ISP headers, which I'm glad we did. We talked about perfboard, protoboard. We talked about big and small microprocessors. Okay. Here's a good closing topic for tonight, and it's something we're not going to get. Thanks, Chris. Nice 90 minutes as always. So, you know, that this fade up and down code that's running on our little ATTINY 13 here took about a quarter of the program space that we had available in that little tiny chip. So if you're really trying to stretch things, there are a few basic techniques for optimizing your code for space. And I'm literally just gonna like touch on this briefly. This could be a whole night, but just in case you're curious about people really slamming things into small code, here's some basic techniques. Using the smallest data types you have. So if you have a value that's never going to be bigger than 100, there's no sense in using a 16-bit variable to hold it when an integer or even something even smaller would do. You want to avoid using global variables, and we haven't really talked about variable scoping, but a global variable is essentially a variable you declare at the top of your code that anything can access, whereas a local variable is a value that is developed or used only inside of a function. Global variables, because they could be accessed from anywhere, have to have a more or less permanent slot in the program memory, not program memory, in SRAM, whereas in program memory, a local variable only has to exist in SRAM because as soon as that function is done, that variable can go away. So avoiding globals is a useful thing. Using progmem for constants, we should do a whole night on code optimization someday, but if you have a variable, like you've been looking at all night, if we have our pin variable here, that value is never going to change over the course of my code, and I know that, but because the program doesn't necessarily know that, it has to store that variable in a very limited amount of SRAM, just like any variable that could possibly change. And often when you're doing these constrained programs, you will run out of SRAM, run out of variable storage before you run out of programming space. So one thing I can do, and I might get the syntax wrong here, is use this progmem statement that stores this variable not in SRAM, but either in the EEPROM or in the same space that the program is stored in, the actual code itself. That's what this progmem means. And that just saves you a little bit of that RAM. Oh, and it says this variable must be const. It's going to tell me I'm not allowed to change it if it's going to be stored in that way, but it will let me store it there. So now I'm using... so here, let's actually take that out, and we can compile it twice and learn something. So if I compile it just as a normal integer, it might have optimized it out for me. because I'm using 0 bytes of dynamic memory. But you can see I only have 64 bytes of RAM total, right? So 8-bit values, which is not a whole lot. So moving things into program space can be a really useful way to start saving on that SRAM, if that makes sense. And then one little technique is loop jamming, which is essentially to say that each time you run through a loop, you have to keep track of not only where the loop starts and where the loop stops and which loop you're in and where you're jumping to. So there's a fair amount of overhead associated with each loop. If you can ever make 2 loops, whether these are do while loops or for loops, if you can make 2 loops into one, you save a lot of that overhead space. So if you think about, let's say, reading the analog state of a pin 5 times and then setting the state of 5 of the digital pins based on those analog readings. Now you could do a loop that 5 times reads the analog value and stores them in, and then a separate loop that writes them to the digital pins. But having that as 2 separate loops actually wastes a fair amount of program space. If you can make those into one loop where you read an analog value, then write a digital pin, then read, then write. By doing that in one loop instead of 2, you save program space. This is all only if you're really scrunching down into tiny microprocessors. For the Uno, you're rarely going to run out of program space in a standard program, so I wouldn't worry about it. This is really more if you're curious. And there's some links in the slides for resources for optimizing code. They're kind of interesting, I thought, so take a read if you want to. Low power mode we should spend a whole other time on, but there's various parts of the oh, interesting. Yep, Palmer points out you use 10% less memory to that demo. Yeah, I think partly that has to do with the const keyword. If things are constant, often your compiler will assign them not just as variables, but actually will basically go through your program and everywhere it sees the symbol pin will replace it with the hard value 0, and that can save program space because you're not storing a variable at all. So in this case, storing an integer I think is muddying my example here. But yeah, just to put a button on low power modes, like here's a little list of like various things in the program that draw power. And like I say, if you're doing any kind of significant output at any given time, it's going to be the primary power draw. You know, if you have an LED on all the time. But if you're in a situation where you have something happening briefly every second or every minute or every hour, you really start to care about how much current am I pulling in the meantime. And so by shutting down some of these things, like actually running code, like running these timers to do peripherals, like using their serial port, these various inter-chip interfaces, by shutting them down, we can save some of that power, really get down into the microamps range of things. So that is the gist of it. For tonight, that is sort of like the process of not only taking your Arduino project and turning it into something smaller and more permanent and putting it on a breadboard, but also how you might scale down from something like an ATMEGA 328 to an ATTINY 44 to something like the ATTINY 13, which is small and tiny, but cheap and plentiful and compact, and that might be a better option for your project. I think that's the whole evening. I think that's the whole curriculum. Test will be on Tuesday, open book. Chris says, where do we go from here? What's next? That's a good question. I feel like I ran into this a couple weeks ago too. I'm not entirely sure where to go next. We had some great suggestions a few weeks ago from folks that I sort of collated. Low power modes and like low power stuff is a possibility. I thought about doing that since we've talked about batteries. That might be kind of a fun to like do a program that like idles and sleeps for a little while. I'm not for next week specifically. I'm not sure I could get set up to talk about like wireless communication, which would be a really cool topic. But I think it might take me a couple of weeks to get into. There's some really good off-the-shelf options. And some of them are fairly powerful, and I want to make sure I do them justice because they're really cool. We could talk about circuit boards. We could talk about PCBs. I'm just spitballing now, so if you're like, ooh, yes, or ooh, no, let me know. We could talk about like circuit boards and construction. We could talk about... I'll tell you one dream project, and then I'm going to tell you the obvious flaw in it. Is we talked about it like 3 weeks ago when we started jamming on some of these ideas, is the idea that we might branch out just a little bit from Arduino into sort of related things. And one thing that made me think of is like, if we could talk just a little bit about writing code on your computer that could interface with code on the Arduino. And now that I say it out loud, so I have been thinking about Python as the language to do that, but I think the more logical language to use is actually processing, which is another project that's a derivative of the wiring project, but the same folks who developed the Arduino interface, or offshoots of the same thing, that's sort of designed to communicate with physical boards. That might be kind of interesting, like, because it allows you to like take readings from your Arduino and get them into the computer and store them as a CSV or an Excel file, do visualizations on them, build little GUIs, like little buttons and clicks of things to control. So that might be an option. Palmer says spend a little time on shields. Yeah. Overview of where we could find them, what kinds of things they can do. Yep. Arduino to Arduino communication, both wired, shields, and Ethernet and wireless. Yeah, Chris, it's a good topic. And honestly, it might be too big of a topic for a single night, because like if we talked about serial a little bit. We talked about serial, I2C, SPI, RJ45, not RJ45, RS45, RS232, Ethernet, and Wi-Fi Ethernet-like things. Like it's a big old topic, but it would be really cool. Sometime, just as like a vanity night, we're going to talk about DMX, because like that's what a lot of my projects use, which for the non-lighting humans is a lighting control protocol based on RS45. That might be a fun night, because I know there's some theater nerds in the audience, and also because it's a good lead into talking about physical intercommunication protocols. Would be really cool. It's like a good way to like introduce some concepts, and if people do have a little familiarity with DMX, that would be like a useful breeding ground. Yeah. Overview, Palmer here. Overview of shields is an interesting idea. I wonder, like so much of this, like especially at this hobbyist level, is here's a thing that you didn't know, I didn't know existed, but solves my problem. And if I only know it existed, it'd be perfect. How do I find out what things exist? I wonder what the interesting way to do that is, rather than just like sitting here showing you things on Amazon, which we just do next Sunday from Micro Center. That'd be fine. Chris says DMX shield versus a way to do it off the shield. Yeah. You certainly you don't need the shield. I'll share with you, just as long as I'm talking vanity projects. My project that's on the workbench this week is a return to my DMX controlled mini moving light project that I had so long ago. Let me find where my little guide went. Where'd my little programming board go? So I've lost a little. Oh, here it is. It's hidden. So speaking of things that are needed, it actually kind of ties right into what we've been talking about tonight. So this little circuit board has a little ATMEGA 328 on it in a little tiny surface mount form factor. It will have a little DMX transceiver on it, and some servo outputs and some lighting driving. So you really don't need a whole shield to drive it. You just need a few critical parts. So we could talk about DMX and how you receive it into an Arduino at some point. That might be kind of fun. I'm not sure if I'm going to make a call tonight. I think it might need to bear a little thought, and really just like all of these are exciting. Might just have to think about a little bit about logistics on my end, and also how to make them interesting. Like I really think, Palma, you've sort of sparked something in me, as like there is so much of this, I think, especially, sitting at home doing this stuff. It's like, oh, that's a cool thing. I didn't know that existed. Like solder wick, like stuff that gets solder off of things. Didn't know it existed. Love it now. But someone had to tell me. And so like, is there some way of like just like cruising through a bunch of interesting stuff? Maybe, or maybe that's boring. Maybe it's just more interesting to like find the interesting stuff as we need it. That might be kind of fun. But yeah, I might delay tonight, and I'll put it up. We'll see. So I guess we'll do, by way of wrapping up, if you're interested in what we're going to be doing next week, as much as I am, because I am too, and you haven't seen it before, you can find all the information about this series, all the slides, all the circuits, and all the code on the website at jeff.glass/electronicsbash. There'll be a page there for each episode. You can find, if you click the link and subscribe, you will get notified whenever there's a video or a stream coming up. If you have questions, please feel free to leave them in the comments of this video. That's a really easy place for me to find them. Or for more timely things, on Twitter, at JeffersGlass is me. And we'll do something fun next week. Intercommunication, maybe processing. I know it's a little bit of a departure, but there's some, now that we've got like a lot of like intercommunication devices under our belt, it might be fun to start building ways that we could, like, you know, not just control the color of LEDs from a little touchscreen or a little, you know, LCD display, but control them from a GUI on the computer, or have a little status bar on our computer that, you know, for Arduino has a temperature sensor and a light sensor and various things. We could make a little weather display that shows up on the screen of the computer that communicates those values to us in a more cromulent way. Might be kind of fun. Might not. Processing, DMX, intercommunication, lots of stuff on the table. We'll figure it out by next week, and we'll go from there. Yeah, look for the posting, look for the tweets, look for the things on YouTube and on the website. Thank you all so much for hanging out with me on another wonderful Sunday night. I hope you are staying well. I hope you're washing your hands. I hope you are looking out for the people in your communities who really need it right now. It is I don't need to tell you, anyone who's in America right now, that it is a wild time, and I feel incredibly grateful to come together with you on Sunday nights and just have a little bit of escape and talk about this stuff, and I like it a lot, and I know that you are all good people and that you are taking care of each other and helping where you can and donating where you can and doing good stuff out in the world, because you're all great, and I know that because you're here hanging out with us. Thank you so much. Be well, and I will see you next week. Thanks.